So somehow we are trying to encourage people to tell them the benefits of nuclear technology and the options they have, the addressing the issue of climate change altogether, and also so in a way we are covering the entire range of sustainability, if you say. So that is the main idea behind IYNS.
Living in harmony with nature has been one of the foundational guiding principles of a lifestyle, especially of India, from times immemorial. Yes, industrialization, which is also a necessary evil, has had its impact. But what has not really caught the attention of all members of the society uniformly is that there can be achieved a balance through mindful living.
That of life. When we live on earth, the very reason why we were born, so for our existence itself, we need to seriously work upon, if not reducing the consumption, then recycling, reducing the wastage, and also ensuring that there is an optimum utilization of energy and in a sustainable manner. That's very important.
We are on a decline. I don't know the facts. I don't know data, whether we'd be able to sustain it. So I won't be able to tell you 10 years or 20. That kind of doomsday call I can't make. But as an educator, as a human being, my assumption and the observation is that course correction was needed yesterday. It is so imperative in the way we behave towards nature. And this is a strong message for our young children in our care, entrusted to us. Let us begin with at least the children who are in our care in Shiv Nadar School.
This topic of nuclear energy sustainability is very relevant to our existence, and we need to have the correct informed information. And how amazing when we can get experts in the field to actually become teachers and to interact and become mentors and coaches. So I think the whole platform needs changing from the school mindset where you used to go to school, get content just given to you, not even challenged the content, and all you were expected to do is perform in an exam. This is a very different paradigm where you're actually thinking more than an exam. You're thinking about your own future, and possibly, as you alluded to, how can I contribute to that future, be it in your own studies, be it even in, and students will not just do formal studies, they'll be involved with startups, non-profit organisations. There'll be so many ways where they can help their community. So I think this is where schools need to change, and I think this whole boot camp and this particular topic is just a fantastic example to show the world of how it could be done.
Fundamentals of what we have actually learned in the science is already the base, but an application, what lacks is the application towards nuclear industry. This is the major research the students can actually dwell upon. So yes, my experience is, so that is a research, and if you actually find a solution to that, that is a technology. So research and technology, this can be coined as, basically two sides of same coin. Once you understand how things work, that can be used in any application, and that can be termed as a technology for that application.
Is to be used, there is no doubt about it. It will be need-based, and then we need to differentiate between where is need, where is comfort, and where is we need to see that we minimize our requirement. We use the best possible energy efficient measures and devices, and more importantly, which I feel every day when I take a round of the school or otherwise, that we need to ensure that there is a zero waste.
Nuclear science, in the past it was there. Right now it is still there, and it is holding a very strong position even at the global level. right? So people are aware there is recognition of nuclear science and nuclear technology. People are aware that nuclear science has a positive application. It is being applied in many fields, whether it's medical, in the medical field where it's being used for treatment of cancers, and then radiation therapy. Then in the agricultural field, the applications are there where the crops are being modified such that they give us more. The yield is more. So yeah, so the application of science and technology, nuclear science and technology, it is there, and right now it's holding very strong position.
A scientific awareness to me is recognizing the importance of science and education in the formation of attitude and making decisions. Now, this is where scientific awareness for me comes in education. And unfortunately, because of the rigor of academia or because of what is really expected as an end goal, a scientific awareness is generally misconstrued.
I think man has always thought that they are the superior species, and it is in their hands that conservation will also happen. And this present COVID-19 has shown us how nature just locked us up in our houses for 15 days, and the earth was greener, the birds were happier. We need to, yes, start thinking of it, but we need to look at nature also for solutions, because at school we talk a lot about ecosophy. Ecosophy means it's the wisdom of Mother Earth. We shouldn't be thinking that we are at the top of the food chain or top of the species where intelligence is concerned. We need to move out of nature's way. We need to find solutions from nature. We need to find solutions which are going to conserve our biodiversity and not ruin it. Because like Gandhiji has said, the earth has enough of every man's need, but not enough for every man's need.
Good morning, everyone, and welcome to day 2 of Energy Bootcamp. My name is Sachit Sharma. I'm a student of grade 11 and also the academic head for the current session. It's a pleasure to be heading today's proceedings among eminent scientists and a very interactive young audience. A heartfelt welcome to Ms. Monica Sagar, Principal Shiv Nadar School, Gurugram, Ms. Nutan Singh, Principal Vidyagyan Sitapur, Mr. Ganesh V, Dr. Vaishnavi Tiwari, Dr. Joyita Sinha, and Dr. Mukesh Kumar Dhiman.
Good morning. My name is Sia Ramanathan, and I will be hosting today's event along with Sachit. Yesterday's session were indeed an incredible learning opportunity for each one of us, as they gave us a holistic overview of the ideas and technologies that nuclear science entails. Today, we dive deeper into the functioning of nuclear reactors, learn about the diverse applications of nuclear science, and have enriching conversations with experts from the field. We'll also take a virtual tour of the Tarapur Fission Reactor Mumbai and ITER fusion plant in France, So before we head straight into the thought-provoking activities of day 2, I would like to invite Ms. Nutan Singh, Principal of Vidyagyan Sitapur, to share a few words. Ma'am.
Hello. Yeah, good morning, everyone.
Good morning, ma'am.
Yeah, it's such a delight to address you all today. And I believe that EBC itself has been a very efficient energy booster, pumping loads of dynamism and passion in all of us. In fact, I was thinking about it and I coined a 2-letter word for it. I thought of very appropriate, which could be associated with this camp. And the 2-letter word is fusion synergy. So there is a fusion of all the ideas and there is that synergy together. And out of it is born this immense strength and the new ideas coming up. So that's my feedback in a nutshell. I would begin by sharing a few voices of students and teachers from my school that I have received in the past few days. IYNS Energy Bootcamp has been an absolutely amazing and enlightening program. Various activities and sessions conducted till now have been extremely informative. The interaction with the scientists working in the field of new energy has broadened my thoughts. That's one of the students. I could understand how nuclear energy could be such significant source of sustainable energy to fight against climatic change and develop advanced clean energy system for the future. For the students who are interested in research work, there is a wide scope in this field. Students can opt for various careers related to nuclear energy. Nuclear engineering is an upcoming one for the students. While working on my project and video, I explored many things about nuclear energy for the video activity, which I interacted with the people of my village. I could analyze that most of the people have misunderstood nuclear energy. I believe that this misconception about nuclear energy needs to be changed and people should also know about its advantages. Through IYNS Energy Bootcamp, we as a participant can try to change the misconception of the people to a certain extent. I feel that our books should also include content related to it so that the concept is clear right from the school level. We are looking forward to upcoming activities to enhance our knowledge about nuclear energy. So that's what the children had to say, and quite a lot, but there's a few points that I took up to share with all of you. I happened to see a picture a few days ago, and underneath it was the information that if you happen to visit the Peace Park at Nagasaki, you would find a 10-meter tall peace statue with his right hand raised high up in the air, warning us of the nuclear destruction. And the second one shows its desire for peace, with eyes closed in prayer and meditation. There is a second scenario, and that's after Chernobyl and Fukushima disasters. After such kind of disasters, it was but natural for the globe to think anti-nuke. A common man, even to this day, dreads or has the misconception of whether to go for nuclear energy or not, with all the drawbacks which he or she thinks has in the mind. So there are certain questions to it. And the fact was that this word nuclear got synonymous with apocalypse. Was it like opening the Pandora's box? Should we keep it shut? Is it, I thought, another narrative from Aladdin's story? And should the genie be bottled up, or could we control it and use it for the benefit of mankind? The third one, again, was like the Kalyanag from the Hindu mythology, and Krishna riding over it, controlling it, and playing the flute. So these were the 2 or 3 images that just one by one flashed, and I thought I will definitely share it with you, and must have been in different perspectives, condition the minds of the people when such disasters took place. Over the passage of time, the views have changed, and the scientists have worked on it, and yes, we can control, I believe, this Frankenstein to use it to our benefit. We could ride on the Kalyanag, we can use the genie to our advantage. In this context, I believe that IYNS in association with SNS through the boot camp is playing such a crucial role, especially of opening not only the young minds, but our minds as well, giving wide exposure and handholding for which we are extremely grateful. The world requires definitely energy to survive, because energy is life. And we need energy, which is cheap, which is clean, which is quick, and which is safe. And the answer to it would be nuclear energy. This program definitely will help the students and to get rid of the myths, spread this kind of an awareness, which they've already done it in their villages. Think of out-of-box solution to fix these problems in future with the least harm to Mother Earth. Fundamentally, what is required is to change the way we think, and the scientists definitely feel that nuclear energy is more of a psychological problem. We can go green, we can be environment friendly, even when we are pro-nuke. There can be nuclear energy without killing the environment. The EBC has been buzzing with activities that are thrilling for both students and teachers. I think for me as well, in the background, the program's success lies in the systematic planning and its execution, and the science staff from all the schools under the canopy of Shiv Nadar Foundation has worked really, really hard for it. For the same, I would like to thank Ms. Ruchi Batra from SNS Gurgaon, Mayank Agnihotri from Sitapur, Megha Bora from SNS Faridabad, Anamika and Rachna from SNS Noida. And of course, all under the oozing, passionate leadership of Vinita Sharat. The reason being is, I just now observed, I logged in a little before time, and I could see how passionately she was instructing and guiding today's comparers. To be able to reach out to scientists and work under their able guidance is a dream come true for students. Today's highlight is the exciting virtual visit to nuclear facilities, both fusion and fission, from Tarapur atomic plant, Mumbai to France ITR. For the same, I thank Dr. Nitendra, President, IYNS, and his team. We look forward to today's presenters, Mr. Ganesh V, Dr. Vaishnavi Tiwari, Dr. Joyita Sinha, for the upcoming presentations and interactive sessions. Lastly, in W.B. Rand's words, a very old poem, but then it's an evergreen one. The last lines that I remember and I would like to share today before I close is that though we are such a dot compared to this earth, we can love and think. And if thinking can make all that difference, let's think right. Have a wonderful day. Thank you. Thank you very much.
Thank you, ma'am, for the encouraging words.
Right.
I now call upon Miss Monica Sagar, Principal of Shiv Nadar School, Gurugram, to share her perspective on the Energy Bootcamp.
May I pitch in here, Sachit, with your permission?
Yes, ma'am.
So Monica ma'am has just WhatsApp me. There is some internet issue. So she said, as I joined, please give me some time to speak. So you can go with the flow of the day with the feedback from Sitapur. Over to you, Sachit and Sia. Thank you.
So before we begin with the activities and sessions planned, let us begin this day on a very positive note by listening to some feedback from students of Vidya Gyan.
Sachit, I feel the video is muted. Harsh video.
Just a second, ma'am. I'll just see to it.
Sure.
So let us begin. Okay. I hope it's all right now.
I attended. Of the day. Greetings of the day to everyone. I'm Harsh Kumar, a class 12 student from Vidya Gyan School, Sitapur. I'm feeling honored for sharing the experience of the workshops I attended. In the first workshop, where I learned about polarity of the compounds and other properties, where we made a galaxy using salt, sugar, soap, and water. And in the next, which was about the pressure cooker, where we learned that by adding salt to water, the elevation in boiling point takes place, which we have already learned in class 12. This helps us in cooking our rice quickly, and which even saves our gas as well as our time. And at last but not least, I would give a big thanks to Nicholas sir and to the whole IYNS team for giving us this opportunity to learn such great things and making our bookish knowledge much helpful for our daily needs. Thank you, everyone.
I'm Jyotsna Pandya of Vidya Gyan Sitapur. First of all, I would like to extend my sincere gratitude to all the IYNS members for organizing the Energy Bootcamp workshop, which was full of learnings and opportunities. All the activities organized during the workshop helped us to understand the complex studies of classroom into simple practical uses. The demonstration of how cooking of rice in salty water using a pressure cooker by Nicholas was superb. Though I had learned the concept, elevation of boiling point in colligative properties, but this demonstration made it simple and interesting. Also, I cannot forget the formation of galaxy experiment, which was a new learning for me. Though the concepts were familiar, but the experiment was totally a new discovery. The IYNS scientists have made us to cherish wonder of science with each breath we do take in this universe. Thank you, IYNS.
Peaceful utilization of nuclear technology is helping mitigate climate change, enhance food security, trace water pollution, and combat acidification of oceans. The applications of nuclear technology lie in diverse areas, including space exploration, medical and environmental science, and agriculture. Therefore, member states are investing heavily on nuclear research and equipment.
To better understand how these applications are revolutionizing the disciplines around us, I would like to invite Mr. Ganesh, who's an expert in the field. Mr. Ganesh works as a scientific officer in BARC. He completed his bachelor's degree in mechanical engineering from VGTI Mumbai and his master's degree in mechanical engineering from HBNI Mumbai. His main areas of work are design and development of equipment in the domains of nuclear and solar energy. Sir, I request you to take the session forward.
Hello.
Yes, sir.
Am I visible?
Yes, sir.
Yes, sir.
Yeah, great. So can we start now or should we wait for a few minutes?
We can start, sir.
Okay, great. So I'll start my screen sharing. So my screen is visible now?
Yes, sir. Yes, Ganesh, sir.
Yeah, great. So, so thank you all for joining in on this Saturday morning. We have been reading and hearing about nuclear technology and projects on nuclear technology and nuclear power for so long. So now I'll be talking about nuclear technology applications, mainly societal applications. So let us dive right in. So as we all know, nuclear technology has an important application, which is producing power and giving us power in the cities, powering our homes, etc. But there is another facet of nuclear technology that we don't know about, or many of us won't know about. And that all stems from the fact that nuclear force is very unique in the sense that it can modify the nucleus of an atom. So as we can see here, this is the nuclear power schematic, and this is a nuclear force which impacts the atom. So this impacts the atom, gives rise to all the applications that we are now going to see forthwith. So my presentation would basically cover these aspects. What are the basics of radioisotopes, the basic functioning, the medical applications, agricultural applications, food preservation, transportation, space exploration, and other important areas. So you might be wondering whether nuclear technology has impact on all these aspects of our day-to-day lives, but we'll go to the truth. Yeah, we'll see what is happening. So let us see what radioisotopes are. So what is radioisotope? Radioisotope is nothing but radio plus isotopes. So isotopes, as we all know, is a chemically equivalent variant of the same element, which has the same number of protons but different neutrons. So the isotope is basically chemically equivalent but physically different. And radio here signifies that the nucleus is unstable, which results into radioactivity. So any nucleus that is unstable can decay into three parts. One is alpha decay, one is beta decay, and one is gamma decay. So as we can see over here, there are three and more possible, but right now we'll be targeting only on these three aspects of radioactive decay. So this one property of radioactivity is enough for all the applications that we are now going to see forthwith. So everything that we are going to see from here on just stems from this fact that radioactive decay is possible in this universe. Only this physical aspect of radioactive decay is enough for us for getting all these benefits, deriving all these benefits. So I must right now say that few radioisotopes exist naturally, but bulk of what we need is mainly made through nuclear reactors. So let us dive right in. So medical applications. So medical applications in this is that we will go first to the medical application, that is treating tumors. Gamma knife surgery. 1 second, just hold on for a second. Thanks for the disturbance. I think one of the slide has been missed over here. Yeah, 1 second. So yeah, so where are we? Yeah. So medical applications come from knowing our isotopes. So the isotopes that we were seeing earlier should have an half-life. What is half-life? Half-life is nothing but the time for which the radioactivity decreases in half. So the half-life should be in range of hours so that the radioisotope doesn't impact our body, and we can readily use the radioisotope for use daily application, and should have gamma rays just for sufficient energy so that we can detect those gamma rays, and should have the ability to be incorporated into chemically active substances, and which means that the radioisotope should be readily incorporated into our chemicals, and it should be readily absorbed by the body. And we can see that technetium-99 is the most widely used radiopharma for diagnostics. So this is just a template for you to decide what isotopes you can use for for your applications going forward. There are other applications for as far as medical applications go. We can use nuclear medicine for treating tumors. So gamma knife surgery, what we can see over here is there are three you can say lenses projecting onto the body, which can be used to remove the tumor. Each particular lens cannot affect the body in any way, but when they all concentrate into one small area, the tumor is ablated. In the sense, it is removed from the body. So right now we are seeing only 3 such focusing points, but in effect there are 200 such focusing points for us to effectively remove the tumor from the body. And this is an external application in the sense the gamma rays are used externally. Internally also we can use radionuclides for removing tumors. So iodine, as we all know, is preferentially absorbed by the thyroid. So when the iodine is introduced in the body, iodine-131 is a radioactive substance. It will get deposited into the thyroid, and if if a patient has a thyroid cancer, the iodine will affect only that particular small area of thyroid where the problem is there, and it won't affect any other living tissue. So this is a very targeted application that can be used for treating tumors. So let us now go to agricultural application. So agricultural application is one particular area where nuclear technology is being used widely, which we may not know, which many of us may not know. So one particular such technique is sterile insect technique. So let us divide this sterile insect technique into 3 parts. Sterile means sterile is nothing but it cannot reproduce successfully. Insects are insects, and technique is used which combines all these methodologies into one particular application wherein we can effectively use for insect control and pest control. So what happens is that we typically start by breeding all the insects, and the male of this species, say suppose a tsetse fly or any other species which causes trouble, is specifically isolated, and the males are sterilized so that they cannot reproduce. The sterile male is now introduced into the general population. So the sterile male then reproduces with the female of the species, and but the eggs that are produced from the females are not viable. In the sense, they cannot go into the next generation. So this is a beautiful technique which combines all the possible advantages which we can derive or which we can hope for. So what we know is that for pest control or insect control, we generally use insecticides or pesticides. And these insecticides or pesticides are costly, one. They secondly are very environmentally degrading. They affect the soil, they affect the crops, and they have a lot of other side effects, as in the farmer that uses the pesticide, if they don't use adequate precautions, they may have skin cancer, or they may develop skin infections, and so on. So this particular this major disadvantage of insecticides and pesticides are removed completely by the sterile insect technique. So what we use here is non-replicating insects, in the sense that any insect that we introduce into the population, general population, cannot by design cannot go into the next generation. So it is a very beautiful technique in that sense. And we are not using non-native species. So generally there are some experiments that were done. For example, in Australia or in Hawaii, some kind of frogs were used, which were not endemic to that region, and they were introduced to control the insects basically. But the frogs, they couldn't jump as high as the sugarcane shoot. So the insect that was affecting the sugarcane plant was generally on the higher side, on the topmost part of the sugarcane plant. But the frog, since it couldn't jump to that height, it was not effective at all. Moreover, what it did was it started affecting the other frogs that were living in the area. So this particular frog not only affected the other frogs which were earlier helping in the pest control, but it started replicating into the area, and basically the problem compounded instead of the problem solving. So this non-native species not being introduced into the system is a very big advantage, because we don't know the second order or the third order effects that any particular thing that we introduce into the nature may cause. And it impacts only the pest reproductive cycle, and it is very species specific, as we saw. So this particular application, although I'm referring here as an agricultural application, it has very important implication in disease control as well. So as we know, malaria that is caused by Aedes mosquito, or tsetse fly, which causes a lot of problems in Africa. So there are a lot of IAA programs, WHO, World Health Organization programs, which uses these sterile insect techniques to precisely target these areas, wherein a very effective very cost-effective method and very environmentally friendly method of treating all the problems that these insects or pests may cause. We go now to the next particular application, that is food irradiation. So food irradiation, as you may all know, is nothing but using gamma rays to kill all the bacteria which reside in a particular food, which causes the decomposition or the spoilage of the food. So sprout inhibition. Sprout inhibition is used mainly in potatoes. So potatoes, as we all know, cause these little sprouts, and if we are able to inhibit those sprouts, the shelf life of the potatoes will increase. Insect disinfectation is nothing but whatever insects may be residing inside the fruit or the vegetable can be effectively killed by using these gamma rays. Shelf life obviously is extended by way of all these methods. And pathogens which we cannot see or which cannot be washed off easily or also killed. As we can see in the beautiful strawberry over here, gamma rays are used to kill all the bacteria residing on the surface. So this you may all know or may not know has been used to treat Alfonso mangoes or beloved Alfonso mangoes for a long time. Many European countries or American continent countries like Canada or USA mandate that all the fruits or the vegetables or many fruits and vegetables that land in their shores have to be irradiated by these kind of facilities. So not only does it improve the farmer's income or go a long way in improving the shelf life or reducing the fluctuation in the price and all. It has also enabled us to export a lot of our produce to other countries and earn us foreign exchange. So this food irradiation doesn't affect the nutrient quality of the product in any way, because it just affects the living organisms and the tissues inside the fruit or the vegetable. So we get two benefits in one strike. In the sense, all the disadvantages or the negative parts of the fruits and the vegetables are destroyed, and we retain the nutrients, vitamins, etc., without causing them any harm. So this is the aspect of food irradiation that a nuclear isotope. So typically, cobalt-60 or cesium, etc., are used as food irradiators. So this over here is the source. This source, puts off gamma rays into this irradiation room. This is typically shielded, and these are used to unload and load the foodstuff that we need irradiated. So next we come to transportation aspect of the nuclear technology. So we all know ships typically use diesel power to transport all the ship containers, or the big ship containers that we see nowadays. Typically use diesel or oil, ship marine oil, that is so called marine oil, to propel them. But nuclear power, it has been used for a long time for propelling ships. So the typical advantage of nuclear power in this sense is that it can be used, the transportation, the ships can be used without refueling for a long time. Refueling in the sense, we need not put in marine oil or diesel or any other fossil fuel. Second of all, it doesn't cause pollution. So as you all know, any pollution caused in the sea is going to directly go into the ocean. So any leakage or any oil leakage will directly seep into the ocean and cause a lot of trouble to the marine life. So that is avoided. And we can use submarine marine propulsion. So submarines also use diesel. So diesel, as we all know, need air to burn it. So submarines have to typically surface to have to come up to the top of the sea to suck in all the air, and then they dive right in to the depth of the ocean. But if we use nuclear powered submarines, this problem is resolved. As in, the nuclear powered submarines can stay inside the depths of the ocean for months and months together without even getting detected. The third application, this icebreakers. So icebreakers are nothing but these are typically used in Arctic circles. So Russia has very powerful icebreakers. So what these icebreakers do is that they, in the winter seasons, they go before the typical shipping containers, and they break all the ice that is in between, is in front of them. So Europe to America, or Europe to China, Russia to China, these particular trade routes are established by use of these icebreakers in the winter months. So these icebreakers are very powerful, and you must be thinking the Titanic was was sunk by an iceberg. But these icebreakers are meant for breaking such vast pieces of ice. They are that powerful. So this is possible only because of nuclear power. And the fourth application is a military application, that is aircraft carriers. These aircraft carriers are very huge. I mean, they are very huge. All the major military programs or military enabled countries like America, Russia have these aircraft carriers. And these aircraft carriers have to be typically at sea for a long time. So they typically use nuclear power. Other than nuclear power, there is very little option that these massive ships can deploy. So there is another aspect of transportation that is now coming up very rapidly in this world. So one of this we know is that fossil fuel powered automobiles are getting replaced in a very big way by use of electric vehicles. There is one other technology that is being used right now, that is hydrogen powered automobiles. Japan is an innovator and a leading pathbreaker in this area. So what they use is that they use hydrogen tanks instead of an electric battery. They use an hydrogen tank for typically powering these automobiles. So this hydrogen is produced from a nuclear power. So whenever nuclear power plant is not working, or it is not being used to the optimal extent, we can use electrolysis or heat-enabled electrolysis or steam electrolysis. There are a lot of techniques that are available to produce hydrogen from nuclear power. And we use this hydrogen to be deployed into automobiles. So hydrogen, when it is used in an automobile, uses a fuel cell. So hydrogen and oxygen combine in a fuel cell, and the byproduct, you may not believe, is water. So when we use fossil fuel, the byproduct that we get is carbon dioxide, which causes global warming. But when we use hydrogen as our fuel, the byproduct is pure water. And needless to say, this doesn't cause any pollution. So, and one more advantage of hydrogen is that it is very energy dense. Typically filled tank, a fully filled tank of hydrogen can go much longer than a typically fully filled petrol tank. So it has a basic massive advantage. There are of course disadvantages that are being resolved now. Engineering is being done as to how to safely transport hydrogen, how to compress hydrogen into small space. Those are engineering challenges that are being resolved. But I am just pointing out to the application that nuclear technology can provide going forward into the future. Now we come to space exploration. So right now I have put two particular images over here. So one is satellite on the left hand side of your of the slide. You can see a typical satellite that is used for communication, for space, for meteorology, for knowing about the climate and all. So this typically orbits the Earth. On the right hand side, I have put a space probe like Cassini or New Horizon, which go very far into the solar system. Like Cassini went into the Saturn and went to Saturn and saw what the Saturn moons look like. New Horizons is now in Kuiper belt. That is, it has now officially crossed the solar system. So what is the difference that you can see over in these two pictures? I'll just give a brief moment for you to think. So there is a main difference that you can see in these two pictures. Okay, so I'll tell you the main difference. The main difference is the use of solar panels. So satellites use solar panels for producing electricity and establishing communication with Earth, whereas space probes cannot use solar panels. It is not as if we cannot put them solar panels into the space probes, but putting solar panels into space probes is worthless, because as we go away from the sun, the amount of energy, amount of solar rays that are incident on the solar panel is very less. So we cannot derive electricity in a space probe just by using solar panels. So what we use over here is RTGs. So RTGs are nothing but thermoelectric effect, Seebeck effect, basically. So RTGs use radioisotopes inside them, and radioisotopes, as we all know, produce heat. So there is a high temperature source, that is radioisotope. There is a cold temperature, that is the space. There is a temperature difference that exists between this high temperature and the cold temperature. And due to this temperature difference, electricity flows. This is called Seebeck effect. This electricity is used for communication, for powering our electronics into the space probes, for keeping the space probe warm, because as we go away from the sun, the space probe becomes cooler and cooler. As we all know, space is very cold. So in these cold conditions, the electronics cannot function properly. So we cannot get all the data that is being gathered into these space probes effectively into our Earth. So for getting all these data to our Earth, what we need to do is that we need to heat all the electronics. We need to power all these electronics. We need to get all the data that has been collected from these electronic systems onto the Earth. So we have antenna systems, we have thermal insulation systems, we have thermoelectric modules, housing, etc., to achieve all these functions. And all these functions are possible only because of radioisotopes. So we use plutonium typically in these aspects. So you might be amazed to know this New Horizon. It was the first probe to do a flyby mission of Pluto, and it has now crossed Pluto. Till Pluto, I guess it has gathered about 5.6 GB of data, and 5.6 GB of data we are able to receive from this amazing space probe only because of RTG, which is possible only because of application of nuclear technology. And these isotopes, mind you, can be produced only in a nuclear reactor. So nuclear reactor, although it does produce power, it also has the capability to produce these isotopes, which we can use in our daily lives. So this technetium that I was talking about, this technetium doesn't exist naturally in Earth. This technetium is basically the origin of the word technetium comes from word technetos, which in Greek means artificial. So we humans have been able to artificially produce elements which we can use in our daily lives to make our daily lives better. And all these has happened only in the past 60, 70 years. So now we go to other applications of nuclear technology, which is carbon dating. So carbon dating is, we are not doing anything in this carbon dating. We are just using the nature given resource of nitrogen 14 and carbon 14 to get to know what the particular fossil age is. And then typically associated with that fossil, we collect other materials like pottery or any other material, and we say that this particular civilization is so and so old, 5,000 years old, 4,000 years old, and so on. So there is no direct application of nuclear technology in this man-made application, but we use nuclear technology or the nuclear physics in this aspect for carbon dating. And other applications we see is that self-powered science. This exit science use tritium inside it. So without electricity, they can work, and they have a very important safety function. On the right-hand side of the picture, you can see a nuclear desalination. So all the all the seawater can be desalinated. We can obtain pure water. There is this another application which is plant-based irradiation. So as we can see, these seeds that are there, we can obtain very large seeds. Groundnut variety that has been obtained here is very big as compared to the natural groundnut variety that we obtain. So this is possible due to nuclear application. So instrument sterilization. So instruments sterilization, as we saw, is we are doing it by using of gamma rays. But sterilization typically has been done by using steam. Steam, as we all know, has very high temperature. It may cause property changes. It has a very high energy requirement, and it has a lot of other disadvantages. So medicine and instrument sterilization like syringes or tablets and all can be effectively done by using nuclear irradiation. Carbon dating we saw. Smoke detectors that we typically see to detect smoke and detect fire. They use americium inside it to detect smoke. When the smoke comes inside, basically an alarm goes off because the circuit inside the smoke detector trips. Plant mutation breeding is nothing but this application that we saw over here. Fertilizer utilization. So fertilizers, as we all know, use nitrogen inside, nitrogen in the fertilizer. So if we have to see nitrogen, how much the plant has taken inside it. So we typically put a nitrogen isotope inside the fertilizer, and we see how much nitrogen that particular isotope has finally gone into the plant. So if we put 100 kilograms of fertilizer, and if 10 kilograms of that nitrogen goes inside the plant, we get to know that 10% is the fertilizer utilization and 90% is going to waste, as in 90% is going to the soil. And pollutant tracking. Pollutant tracking is nothing but, as we all know, the smoke comes out from the chimney. We can put some radioactive isotope inside the smoke, and we can trace it, say 100 kilometers, 200 kilometers. We can say, okay, this much amount of air, in this much amount of air, this much is the pollutant, because we know that this factory has caused this much pollution, and we have introduced so much quantity of radioisotope, and we are able to detect so much isotope over here. Water resource tracking. So as we all know, we are facing massive groundwater depletion, and massive rivers are going dry, and a lot of problems are happening. So we can see how much of the rainwater that is falling on the ground goes into the aquifers or the groundwater source, and we can come up with strategies to improve that particular groundwater resource. So these are very, there are a lot of other applications which I have not enlisted over here. Basically, my point over here is not to dump on you all the applications that I know or that is existing. All that I want to emphasize over here is that nuclear technology has a very important societal application that many of us are not aware about. It's just like a coconut tree. Coconut tree just doesn't give the coconut, the coils, every aspect of coconut tree is beneficial. So a nuclear reactor, not only does it produce power, which we all know, it has so many applications like producing radioisotopes or various radioisotopes which can be used in various facets of our daily life. I just wanted to emphasize those aspects over here, and that completes my presentation. So any question and answer questions you might be having, I'll be happy to take. Yeah, thank you.
Yes, sir. We have a few questions.
Yeah, great. Go ahead.
The first question is, what is radioisotopes?
So yeah, so radioisotope is nothing but we all know isotopes, right? Isotopes are nothing but same element, but different number of protons. So the number of different number of neutrons. The number of protons will be same, but the number of neutrons would be different. So physically they are different, but chemically they are the same. So radioisotopes are nothing but these isotopes. What I can say. So uranium, for example, uranium has 235 or 238, two isotopes which we all know. So uranium 238 is 95%. It is very much abundant, 99.3%, and 0.7% in the environment is uranium 235. So what this means is that uranium as an element is chemically same, but it has two different, physically separate entities. One is uranium 235, which has 235, nucleons in it, and one is uranium 238. So the uranium 238, U238 has 3 extra neutrons in it, and this aspect we use to produce power, to use in various aspects. So radioisotopes are nothing but radioactive isotopes. That's it. I hope I have made it clear.
So the parents won't be able to reproduce. I think this is in reference to sterilization.
Yeah, sterile insect technique. Yeah. Yeah, go ahead. What is the exact question?
So the question is, will the parents not be able to reproduce?
No, the parents will be able to reproduce. The thing is that they will be able to reproduce, but the offspring, the eggs that the insect lays, won't be viable. So the next generation, as you can see over here, the sterile male is released over the target area. They compete with other males to mate with females. These females lay eggs. The eggs are there. They come up in the next generation, but the eggs don't hatch. So what happens is that the female will realize that it is reproducing and it will go through its normal cycle, but the eggs won't hatch, in the sense the next generation won't come up. So the eggs will just decompose. So that is the major advantage of this particular technique. So the reproduction happens, but the next generation doesn't come up.
Thank you, sir. The next question we have is, how do they store the nuclear waste / fuel in the ship? Won't it cause radioactivity?
No. What happens is that these nuclear ships have typically a refueling cycle of ranging in years, so 5-6 years. So what happens is that these fuels are stored in metallic tubes, typically zirconium tubes. So what happens is that once all the power that is able to be extracted from these fuel is extracted, these metallic tubes are removed from those ships and they are safely deposited into a reprocessing area, and these ships are loaded with fresh fuel. So the radioactivity, whatever radioactivity is there, typically always stays inside these metallic containers. So it doesn't come out. It doesn't come out out of these metallic tubes in itself. So 1 second, I'll just show you over here. So these metallic tubes are situated over here. So outside this, there is a reactor vessel. Outside this, there is a containment. Outside this, there is a ship. Okay. So 1 second, we have the ship itself over here. So this is the reactor. This is the primary circuit. This is the reactor compartment, and afterwards, there is the ship. So the radioactivity doesn't come out at all. Yeah, there are a lot of barriers for it.
Thank you, sir. Next question, can beta or alpha rays not be used instead of gamma rays for food irradiation?
Yeah, so what happens is that alpha rays cannot penetrate deep inside any object, and beta rays, so typically if we use a paper sheet, a paper sheet or an aluminum paper sheet is enough for blocking a gamma ray, alpha ray. An aluminum sheet is enough for blocking a beta ray. Okay, gamma rays have the capability to penetrate deep inside the food. So as we all know, say an apple. An apple has a insect deep inside it, or a seed, or an insect egg deep inside it. So we won't be able to kill it with using alpha ray or beta ray. So we have to use gamma rays of sufficient energy so that it can penetrate deep inside the apple and kill whatever the insects or the pathogens are residing inside it. Yeah, this is the gamma ray that is, killing all the bacteria. Yeah.
So I think this is again a similar question. How do gamma rays kill bacteria?
So gamma rays are all gamma rays cannot kill bacteria. Okay, so gamma rays have to be of a sufficient energy to kill the bacteria. So what gamma rays does is that the biology of it is very complicated. I'll just tell the overall aspect of it. So gamma rays, what it does is that it causes cell level changes inside the bacteria. So cell level changes in the sense the protoplasm or the cell fluid that exists inside it, the DNA that exists inside it is changed completely, and you can say the bacteria kind of evaporates from within. So the bacteria or the pathogen is killed in that way. Yeah. So the point over here is the gamma ray has to be of sufficient energy. That is the main aspect that we have to look while using it for irradiation.
Sir, another student is asking, won't electric cars be more efficient than hydrogen power cars?
Efficiency wise, there is a debate because see, it's just not about the efficiency, right? The method of overall efficiency, if we see from an electric battery to the motor, obviously the electric battery wins. But the electricity inside the electric battery doesn't come up from any other source, but the solar or fossil fuel or any other source. So those typically, right from the source to the sink, if we see, the energy, the efficiency doesn't vary much, because the fossil fuel or the solar energy that we use for recharging the battery has very little efficiency. So the main point wherein the wherein the electric vehicle scores over hydrogen vehicle is that batteries are very, they are quite safe as compared to hydrogen powered vehicle. And the complexities, the engineering complexities associated with an electric battery, electric vehicle is typically less as compared to a hydrogen powered vehicle. But the efficiency is not a deciding factor. Cost is a deciding factor. The engineering aspect or the complexities are an deciding factor when going for electric vehicles or hydrogen vehicles. But the efficiency typically is more or less the same.
So the next question is that what is the difference between the heat and cold temperatures?
Heat and
cold temperatures.
With respect to? I guess this is with respect to space exploration. So what I wanted to say is that not heat and cold temperature, hot and cold temperature. So all these radioisotopes, when they emit alpha, beta, or gamma rays, associated with these emission is the temperature production. So they produce heat. So this heat causes rise in temperature. So you can see over here, these are the thermoelectric modules. So these thermoelectric modules, what they have a high, high temperature source. They have a cold temperature source. Cold temperature source is nothing but our space, because space, as we all know, is at very low temperature, 3 Kelvin typically. And these high temperatures are very, high temperatures. So this temperature difference that we see over here causes an electricity to flow. So this electricity that flows, we use for powering the electronics. So it is not heat and cold. It is hot and cold temperature. So this typical temperature difference is what we use for powering these space probes.
Sir, I think we have time for one more question.
Yeah, go ahead.
Won't SIT make the bugs extinct, causing ecological imbalance?
So that is one particular, major advantage. So bugs won't go, extinct, because as we can see, these sterile males are introduced into the population. They compete. So 50%, say 50% of the existing population is now being replaced with these sterile males, and 50% is, reproductively viable. Those are wild males. So these 50% of the wild males that are existing in the population, they will reproduce normally. The only thing is that if suppose 2 becomes 4, 4 becomes 8, 8 becomes 16, what we see is that 2 will remain 2, okay, in the next generation. And the reproduction ability or the exponential growth that we see in the insect population is reduced. But the other aspects, other techniques told you, they cause this problem. As in, if we introduce other species into the system, they cause the other competing species to go extinct. So that is avoided by using this sterile insect technique. Yeah.
Thank you, sir. I'm sure this session has answered some of the leading questions the students have been holding on to.
Yeah, great. So if anybody else has any other questions, please feel free to mail me. I'll answer those questions.
May I speak? So there are many questions, Ganesh sir. It has come to me by WhatsApp, and there are many questions in message box. So collate all those questions, and will request all the people who are asking questions to post these questions at IYNS and Shiv Nadar and school, page.
Yeah, great.
So I've seen you people replying answers within 24 hours or less than 24 hours, sometime immediately. So post that inbox, the IYNS page, so that you can, answer those questions there. Thank you so much, Ganesh.
Yeah, great. Thanks a lot. Thanks a lot. Yeah.
Thank you, sir. Fission reactors have undergone massive improvements since 1956, becoming safer and cheaper. Concerns still exist regarding safety of nuclear energy, finances, and efficiency of waste disposal systems, which is why the evolution of reactors is an ongoing process. At the same time, nuclear scientists are working towards making nuclear fusion power plants a reality, a scientific landmark which will theoretically solve all problems related to energy security. The best way to learn how nuclear energy is harnessed is to witness an actual power plant. Let us get ready for an interactive session by Dr. Vaishnavi Tiwari, who will take us on a virtual tour of the Tarapur Fission Facility in Mumbai. Dr. Vaishnavi is the editor-in-chief at IYNS. She has a PhD in physics from École Polytechnique Université Paris-Saclay in France. Her research focused on modeling and simulation activities related to the severe accidents in light water nuclear reactors. She's also associated with the website Nuclear Energy, The Better Energy, where she is a part of the editorial team. Ma'am, I'd like to thank you for joining us and making this tour a possibility. Over to you.
Hi everyone, am I audible?
Yes, ma'am, you're perfectly audible.
Okay, so good morning to everyone, and just without any delay, let's start our session. Just a minute. Okay, so as you already mentioned, I will be talking about fission technology and reactors today. And I am aware that you have been familiarized with the concept of nuclear decay and radiation during the first lectures of the first day of the Energy Bootcamp. So I would like to start my presentation with a really small cartoon like situation to explain you exactly the concept behind nuclear fission. Now, it's governed by the laws of cartoon physics. And there you imagine that there's a crowded bus which is filled with people. Like, you cannot really add another person or put another thing inside this bus. But there is this person, Mr. N, that wants to enter the bus. And so when he does, the bus starts to, expand and become unstable, ultimately breaking into two pieces and resulting in more people falling out of this bus. Now, you imagine that this bus is actually a heavy uranium nucleus, and Mr. N is in fact a neutron. So now when a neutron interacts with a uranium nucleus, which is already an unstable nucleus, it tends to deform this shape of the nucleus, ultimately ending up in the uranium nucleus splitting into two different nuclei, which are stable compared to the uranium nucleus and are smaller in size. And also, during this process, this entire process results in release of energy in the form of gamma radiations and also the kinetic energy of the fission fragments. So now, on an average, the energy that is released through each of this fission reaction is about 215 MeV. Now, what if I tell you that this energy can actually be used to produce electricity? This is where the concept of a nuclear reactor comes into place. Now, a nuclear reactor, just like any conventional power reactor, which is, let's say, for example, coal. We all know that a lot of India's energy needs are met by coal and petroleum. So, for just like that, any nuclear reactor works on a basic principle where we have a coolant that is, through a chemical process, this coolant is heated and its temperature is raised such that this heated coolant passes to a turbine where it could be in a form of steam or, depending on, it could be, if it's water, then you could, boil the water and pass steam, which can turn the which can turn the turbine and move to the generator that produces electricity. Or if it's, let's say, a pressurized system where, the water will not exactly boil due to a high pressure, but it will just raise its temperature. Or if it's a liquid metal that is being used as the coolant, so that will also not evaporate or, form vaporized metal, but would be a higher temperature liquid metal. So this is basically the concept behind a nuclear reactor. You use this fission reaction. In fact, not just a single fission reaction, but a chain of nuclear uranium atoms being, but a chain of uranium atoms being, broken into smaller fission fragments, and the energy that is released. So let's say 215 MeV per fission, and there's like millions of fission reactions taking place simultaneously. So you use this energy to raise the temperature of the coolant, which in turn drives your turbine and leads to the, converting this, ultimately this chemical energy into electrical energy. Now, if you say that, okay, if the underlying principle is the same, how do you really, say that nuclear energy is better? Now, for this, I will give you just a short description. Like, there's a short comparison between the different, energy densities that are provided by these different energy sources. Now, for example, if you take coal or oil to produce energy, you see that the energy density through these sources is very less. It's of the order of 3 or 4 kilowatt hours per kilogram of coal or oil, respectively. Whereas, if you look at nuclear energy, you see that a single kilogram of uranium, or let's say the nuclear fuel, can give you up to 50,000 kilowatt hours of energy. And if you compare this figure to also the renewable energy sources such as solar and wind energy, you'll see that the comparison is a little difficult in the sense that the solar and wind energy, they actually depend on factors such as the availability of sunlight, and for instance in terms of wind energy, it's the speed of the wind, and also the land requires the requirement that is required for per unit energy production. So now see, we talked about nuclear fuel and how this fission energy is used to generate electricity. But what you have to keep in mind is that not all radioactive materials can be used to generate energy. Now, if we, in terms of energy production, this radioactive materials can be categorized into two different, two different kinds of materials. First is a fissile material, which can actually be used to produce energy directly, as if you if you bombard a fissile material with a neutron, it will undergo fission and release energy. Whereas there's another class of materials which is called a fertile material. Now these materials, they do not undergo fission immediately, but if you add, bombard them with a neutron, they will turn themselves, or in the physics term, it's called transmutate themselves into fissile materials. Now, the examples for these fissile and fertile materials are, as you can see over here. So there's uranium-235, which is the only naturally occurring fissile material in the world. And other than that, you have another isotope, which is uranium-233. And also there is plutonium-239, which is a fissile material. For fertile materials, there is uranium-238, which undergoes mutation to form plutonium-239 when it is bombarded with a neutron. And there is thorium-232, which undergoes mutation into uranium-233, also a fissile material. Okay. Now, speaking about the nuclear energy landscape of India, we should know that in our country, nuclear power is actually the 5th largest source of electricity generation. Yes, I understand that the overall percentage is not as high compared to the coal and petroleum energy sources that are being used in the country right now. But still, given our current path and what is planned for future, with currently 22 operating plants and 7 plants under construction and many more which have been planned in future, I'm pretty sure that nuclear energy will go on to become a major face in India's energy basket. Now, if and all this planning in terms of the number of plants that are operating right now and the number of plants under construction, it has all been it has all been done under the India's 3-stage energy program, nuclear energy program. Now, if you ask about what is the 3-stage nuclear energy program, so this was actually formulated by Dr. Homi Bhabha, and the main reason for having a 3-stage program which is specifically crafted for India is because in India we don't have resources for uranium, the uranium material that we require for nuclear fuel. We don't really have in-home resources for that. Instead, we have abundance of thorium in India. Now, so what this 3-stage program does is that during the first stage, we use the natural uranium, which is basically 0.7% of the fissile 235, uranium-235, and 99% of uranium-238 to produce energy by using this natural uranium fuel in reactors. And as a result of the fission reactions, and also with uranium 238 interacting with the neutrons inside the nuclear reactors, this this during this first stage we also end up producing plutonium 239, which is a fissile material. Now, using this plutonium 239 from stage 1, we enter stage 2, where we use the same material along with depleted uranium, which is actually the 99.3% or maybe less of uranium 238, which was left from natural uranium, to generate electricity, as well as breed more fuel. By breed, I mean that during this stage, the reactors, they contain a security kind of a security blanket. That's a very layman term to use this word security blanket, but a blanket which consists of thorium atoms. It's fabricated out of thorium, and you use the neutrons that are released during the fission reaction to convert this thorium 232 into the fissile material uranium 233. And with this, we move on towards the third stage, which is finally to use thorium-based reactors to generate electricity. Now, by doing this, we are trying to close our nuclear fuel cycle, as well as utilize thorium reserves that we have present in the country, thereby making ourselves self-sufficient in terms of nuclear energy and also in terms of reducing future carbon emissions. Now, with this, I would like to move towards the visit that we have planned, which is actually about the Tarapur nuclear power plant. And what you should know is that Tarapur nuclear power plant was actually India's first commercial nuclear power plant, which is located in Maharashtra. And currently it has 4 reactor units that are operating on a net capacity of about 1400 megawatts. And this is owned and operated by the Nuclear Power Corporation of India Limited. And this video that I'm going to show to you was shot by the National Geographic Channel at the Tarapur facility. And the department has actually been graceful enough to provide us with this exclusive footage of what is going on actually inside a nuclear facility, which is one of the world's heaviest, heavily guarded, heavily guarded facilities that could be ever imagined. So there we go. Without any further delay, I would like to start this visit.
Vaishnavi, we could not see the video yet.
Just a minute. I will try to, start it again. There's a problem. Really sorry.
Thank you.
Yeah. Okay, is it visible now?
Yes.
It's visible, right?
Not your desktop
screen.
I'm sorry, just a minute.
You just shared the
This is the outer containment door, and then there would be one more inner containment door. So before entering, we will put on this protective gear, the gloves and the shoes. Inside right now, our fueling operations are going to start. So I think we will be able to get a view of that also.
There's another door.
Yeah, there's another door. Actually, there are two different containments in this. The whole reactor building is having two containments, the inner containment and the outer containment. And both these two, when there's a differential pressure between here, inside the other door and outside. They are meant to prevent any release of radioactivity to the outside environment. There are two separate set of buildings. One is completely enclosing the other one. So we will just move now to the inner one.
Oh my God. So this is as close to the actual reactor that you can possibly get.
I was about to witness up close what very few people in the world have seen. The actual loading of a fuel bundle just before it is inserted into the reactor for nuclear fission to take place. These new fuel bundles have gone through some stringent quality checks before they arrive here. The raw fuel bundles, which are made in the nuclear fuel complex in Hyderabad, the center which makes all nuclear fuel, are carefully brought to the plant and thoroughly checked for their quality.
After receiving fuel bundles from the manufacturer unit, we are doing the three tests. One is a physical test, then it is a dimensional test, and third is a integrity test. After doing the visual and dimensional checks, we are putting three bundles in one bumming chambers in individual. And after covering it, we are pressurizing this by the helium gas up to 6 kg for 1 hour.
The helium test is used to detect leaks. Once the new fuel bundle passes it, it is good enough to be loaded into the calendar.
Now we are inside this new fuel loading area. It's also one of the critical areas, and from here we will load the fuel manually, and then we will go ahead. This fuel goes after that, it's all through a system driven.
Is it safe for me to handle it?
The new fuel is not, there's no problem in that, and it's visitor friendly, so there's no problem. So I will just lift one of these bundles. It's a bit heavy, and we just have to put it here. The fuel goes in pairs. So would you like to load the other one?
Sure, why not?
Now what you are carrying is 1 million units of electricity. This one fuel bundle.
1 million?
1 million units of electricity.
That's heavy.
I think you are able to lift it quite comfortably.
It's not that easy.
Now here onwards the hydraulic ram will advance, and then the fuel goes into this new fuel magazine, and then again the transfer system, the fueling machine, which we'll be seeing next.
Alright.
So but now we have loaded together, both of us have loaded 2 million units.
2 million units. Let there be light.
Now this is the vault where all the coolant channels are there, in which the uranium fuel is there. So this area is inaccessible, and it is closed by this door, which has got an interlock. It won't open when the reactor is above a particular power, 0.1% power.
Above 1% power.
0.1% power, we can't open it.
So this is one of the two entry points into the vault of the nuclear reactor. You can enter only once the plant is shut down for maintenance.
Inside the radiation fields are significantly high. So outside it's pretty safe. There's no problem over here. So we'll just see from there the wing window. The other side of it we can see inside. This is called the wing window. And from this wing window you can just go inside and see. You can go near, sir, there's no problem out here. And what you're seeing inside is the fueling machine.
This is probably the most futuristic thing I've seen outside of science fiction films. this is the robotic machine that actually loads the fuel.
Yeah, exactly.
What we've just put in there.
Yeah, right. What you have put in here, that is the fresh fuel has come into this machine. It has taken this fuel and now it will be loading into this calandria, or we say the coolant tubes. There are 392 coolant tubes, and each of this machine will just now swing at 90 degree and align with those coolant tubes. Right now he is going to do the first channel of today.
Those things, each one is there basically to maintain a certain temperature. How much what kind of temperature are we talking about?
If you see closely inside, there is a plug outside. We call it the sealing plug or the closure plug. So that inside those tubes, there is a temperature of around 300 degrees centigrade and a pressure of around 100 kg per centimeter square. These refueling operations in this plant, we have now taken out the seal plug and put it back around 7,000 times. That means around 14,000 times we have opened it and put it back. So it's pretty safe. And overall, among the Indian nuclear power plants, we have now done these operations for around 70,000 times. So that much expertise we have developed now.
And all this nuclear energy that is generated finally finds its way to the mammoth turbine room.
I'm now heading into the turbine room. That's the place where electricity is actually generated. But before I go in there, I better put on these earmuffs because I've been told it gets really loud in there. All set?
The production of nuclear electricity is done on a massive scale at Tarapur nuclear power plant. The nuclear energy generated is finally transformed into electricity in the turbine room.
Now this feels like a proper nuclear power plant. I can feel the heat being generated from the steam that is being produced inside the turbine. Behind this turbine, there are two turbo generators. And over there, on that meter, we can see the actual amount of electricity being generated in megawatts.
Once the electricity is generated, it is transported through a transmission network or grid, which are wires that wheel high voltage power over long distances to the substation. The voltage is then stepped down at the substation and then distributed to the end user at voltages suitable for home use. So where does nuclear power score over other forms of energy?
The nuclear power is location neutral. That means the nuclear power plants can be set up at any of the locations irrespective of the availability of the fuel. Another thing is the nuclear power is a base load generating technologies. That means it generates the electricity 24 hours, all 7 days in a week, or you can say 365 days in a year.
Presently, thermal is acting as a base load station. All our thermal resources like coal and petroleum, they are depleting fast. Well, you see that renewables like our solar and wind power, they are supplying electricity intermittently, so they cannot be considered a base load station.
So when it comes to nuclear power, where does India stand?
India has more than 4 decades of safe nuclear power generation, and we have mastered pressurized heavy water reactor technology. We have comprehensive capabilities in designing, construction and operation, and we have demonstrated our capabilities in par with the world-class standards. In fact, one of our reactors is operated more than 750 days continuous operation, which achieved the second longest duration of operation among the world reactors. This shows our competency in par with the world class.
But getting to be world class doesn't just happen. At Tarapur, complex technology is handled by extremely skilled personnel, and it is not by chance that every single person working at Tarapur has got here after a long, intense period of training.
The nuclear reactor is a very big power generating utility. When you are operating nuclear plant, the enormous responsibility of operating this plant in a safe and efficient manner is very huge. And therefore, we have to make sure that every step, starting from induction to training to continual training and field experience, that whatever pool of manpower which we are utilizing for operating this plant are indeed worth it. So that's why we have a very elaborate qualification and licensing program. These licenses are awarded by the Atomic Energy Regulatory Board. Broadly, we recruit at 3 different levels, namely technician, supervisor and scientific officers. Those who are shortlisted from written examination undergo interview. If you clear that interview, then you are just inducted into a rigorous training program. Just like breathing is required all the time, similarly, continual training is part and parcel of operating a nuclear power station. We cannot be complacent that, okay, you are licensed, you can continue to operate. If he is a licensed control engineer, he cannot continue to be so unless he clears himself after 3 years. So there is a requalification every 3 years.
This is the place that turns these men into pros. Under simulated conditions, these men face situations, some of which they are improbable to face during their tenure at the plant. But their extensive training here will prepare them for any eventuality in the future, for real. This is an exact working replica of the control room that trainees get to work with.
Basically, we are having normal day-to-day operation in the plant. These are normal operations. Then infrequent operations, those which do not occur normally. And then some are our emergency operations also. And we give training on all those things. This is a infrequent operation where they do not get an opportunity in live system. So we will simulate a sequence and they will act and take actions as needed as per the scenario. Whenever we give an exercise, basically we evaluate them on 9 parameters. So those parameters are also set. Their attentiveness to panel, their initial actions, their subsequent manual actions, their teamwork and procedure adherence. आज हम एक exercise करेंगे class 4 failure का. And your roles I will just define. You are the assistant chief engineer. You are the overall control of the panels in the station.
So detail to safety and training of personnel is key to running Tarapur successfully. While nuclear power has certain advantages over other sources of power,
people are still wary about nuclear power. In the nuclear world, an accident anywhere is an accident everywhere. And some of these accidents, admittedly, have left their scars on nuclear history. But these very accidents have also provided vital safety lessons for existing nuclear facilities around the world.
In nuclear power technology, we have a good international cooperation. The incidents which happened in the internationally, right from 3 Mile Island accident, Chernobyl accident, and even the recent Fukushima accident, all have been, the internal details have been very well shared among the international community. The experiences gained and the inadequacies, everything has been well analyzed. And in Indian context also, we have taken several measures to strengthen the safety features. We have provided additional features in the new reactors as well as in the existing reactors based on these accidents.
So how safe is this nuclear plant?
Tarapur functions on a defense-in-depth philosophy, which essentially means that there are multiple barriers in place to prevent disasters. It starts with the uranium, which is in ceramic pellet form. These are encased in sealed zirconium alloy tubes to form fuel rods, which in turn are confined within a steel pressure vessel. Finally, this is enclosed in a containment structure with walls nearly 2 meters thick.
If we see the onion, before reaching to the core, there are multi-layers. Similar philosophy is applicable for nuclear power plants. Basically, it is multi-layer prevention, including the physical barrier, to prevent the release of the radioactivity to the environment. The basic aim of the defense in depth philosophy to prevent the accident suppose accident do happen, then we have to limit the consequences and subsequently prevent the progression of the consequences to the environment.
The plant has got a two-group safety concept. With each group of safety independently can cater the various basic safety functions of the nuclear reactor, what we call as 3 C's, that is control of reactivity, overcooling and containment. So each group is capable of performing all these 3 functions. In order to achieve that, the plant layout has been made in such a fashion that half of the safety systems are physically located in an independent structure and half are located in other part of the area of the plant.
The walls of this dome are fortified to ensure that no radioactivity escapes from the inside. Apart from its thickness, there is a second layer of wall with negative pressure between the 2 walls so that in case of a leak, the pressure from the outside prevents the inside radioactive air from leaking out.
We have got these 2 barriers, inner wall and outer wall. If activities, let us say it goes out, then we have got a 1.6 kilometer exclusion zone. Beyond that only, people are permitted to habitate.
Even beyond the fringes of the exclusion zone, a strict vigilance is kept on the radiation effect on the environment. The Department of Atomic Energy has kept a watchdog called the Environmental Survey Laboratory that tests the environment for any traces of harmful nuclear radiation.
We started our work right from 1964, much before the plant started operation. And we were doing for last more than 4 decades. We collect samples like air, water, and milk, fish, vegetable, grass, seawater from this local environment. The primary role of the environmental monitoring is to demonstrate that dose to the members of public is within the limit prescribed by regulatory agency of India based on international guidelines. The Tarapur nuclear power station and other facilities are safe and there is no impact to the environment due to their operation.
Perhaps one of the biggest advantages of nuclear power generation is that there is no emission of greenhouse gases and the surroundings are kept green.
And well, this butterfly park is proof enough. What is happening here?
This is our main spent fuel storage pool of TAPS 3, and there is a similar pool of TAPS 4. In this pool, we can store our reactor fuel for a period of 10 full power years.
You're talking about the bigger pool?
Yeah, the bigger pool.
And these ones?
And these smaller pools are the receiving base. When the fuel comes from the channel, the discharge fuel
from the reactor.
It comes in pairs. 2 bundles come here. We take them, receive them over here, and then we push it down to the bigger pool. And then there we keep them in those storage trays. What you are able to see there are the trays.
Yeah.
So we keep them there stored. This water is for cooling as well as for shielding purpose.
So take a closer look, can we?
All the fuel bundles used in the past few years have found their resting place in this huge pool, more than 30 feet deep, filled with demineralized water. When a fuel bundle is removed, it emits heat and radiation. So to cool the bundle and shield the radiation, it is kept in this pool of water called the spent fuel storage bay. The minimum cooling period is 4 years, after which they may be sent for reprocessing.
What are the chances of this water mixing with, say, groundwater or any other source of water?
The chances are next to negligible. The system is designed in a way, this whole, like what you're saying, there are the SS plates.
SS as in?
Stainless steel plates are there.
Okay, not Secret Service.
There are stainless steel 304 plates, and after, this whole pool is lined with these plates. And behind one layer, there's another layer of plates.
Okay.
And then there are other systems. This whole ground is also 5-meter waterproof. There's a waterproofing treatment also there.
It's probably the most armored of vaults that you
get.
It's
most armored. There have been plenty of quality assurance checks we have done on this, including vacuum box testing, DPT and everything, so that there is no leak from the here. The spent fuel bundles will be coming out from this.
You will actually see the bundle.
Yeah, we will actually be seeing the bundles which we have refueled or discharged from the channel in the morning.
I never dreamt that I would actually witness this kind of a nuclear transfer happening with my naked eyes.
Those are the spent fuel bundles.
Oh. So once again, is it like a shell that I'm seeing, or is it actually the fuel that I'm seeing?
It's actually the fuel. Right now also you can see there is somewhat of a bluish tinge out there on the spent fuel bundles.
So it's not just that they are blue colored, it's a blue glow. It's like emitting light.
Yeah, it's called a Cherenkov light. This is a special peculiar characteristic of a spent fuel bundle. Actually, the speed of the radiative particles in this water medium is more than the speed of light in this medium. Because of that, that bluish tinge is coming.
Oh.
And it was discovered by one scientist, Cherenkov, so it's set on this name.
So unlike a thermal power plant, where the coal cannot be reused, a nuclear power plant uses what is known as spent fuel. So when we see these uranium fuel rods that have been used coming here, they'll be stored in these cases, and eventually plutonium will be extracted from them, which can again be used as nuclear fuel.
India has a 3-stage nuclear program, which was envisioned by the father of the Indian nuclear program, Dr. Homi Bhabha. In stage 1, natural uranium is used as fuel to generate electricity. In addition, plutonium-239 gets generated. In stage 2, plutonium-239 with thorium will be used as fuel to generate electricity. In addition, U-233 will be generated. In stage 3, uranium-233 with thorium will be used as fuel to produce power, as well as more uranium-233. But being dressed like a superhero still doesn't give me superpowers, so I still need to get my radiation levels checked.
Rajagopalan, I've just come from zone 4, and could you tell me how would you measure my exposure to radioactivity if there was any?
Yeah. If there are 2 personal monitors we are given to you, this is called TLD, this is the direct reading dosimeter. So you can see that while taking, the emitter given you at 0. And now you can see the final reading is 2.33 microsievert. This is the dose you have received for today. Microsievert. That is the dose you have received. But this is recorded here also. But similarly, every day you will be taking this when you take a job. You might have taken an RWP for working. And every day, this dose will be added in your TLD number in our software program. So end of the month, we will send this for reading. Whatever the dose registers, that is called the legal date.
What is the permissible limit?
We got 2 types of categories. One is the temporary workers and is a departmental worker. For departmental workers in a year, you can give up to 30 millisievert dose. But for temporary workers, it is 15 millisievert dose. That's the dose limit we are giving for that.
And how do you monitor the different zones? I noticed there are machines everywhere if you go from zone 4 to 1, lower zone.
Yeah, all these areas, all the zoning is based on our radiological probability of contamination. On that basis, we are divided. When you are exiting from each zone, you should check yourself you are not carrying any radiation with you. So that we call it as a contamination. That's why it is called interzonal monitors. It is mandatory that when you exit each zone, you have to thoroughly check for contamination. That's our zonal philosophy and the way we are controlled.
So I've spent an entire day inside the nuclear plant, and I've just been given the green signal. I'm completely contamination free. I must say, I came in with a little bit of reservation, coming into a nuclear plant for the first time. But it seems like any other industrial plant, except that you have to wear this bit of protective clothing, and that's about it.
And as I leave, Tarapur continues its relentless mission of producing power. In the near future, India plans to increase the supply of nuclear electricity multifold. And as the largest power-producing nuclear plant in India, Tarapur will continue to lead the way.
We have some questions in the chat, so we will begin with them. Dr. Vaishnavi, should I ask the first question?
Yes, please go ahead.
So the first question we have is, in a nuclear reactor, the heavier or unstable atoms split into lighter or more stable atoms. What happens after this process? Are these more stable atoms split again into more stable atoms, just like what happens inside the core of a star?
So you mean that the smaller atoms, do they split further, if I understood the question correctly? So not exactly. I mean, see, the concept of chain reaction, I think that's where it is originating from. So the concept of a chain reaction is basically heavier atom splits to form, lighter atoms. Along with that, because these lighter atoms are also kind of they also emit, if they are unstable, they emit the radiations, and then they stabilize, so the energy comes down. And also, as a result of this splitting of the heavy atom, there is a release of more neutrons. And so these neutrons that are released as a result of the fission, they tend to interact with the other heavier atoms, and that's how this chain reaction basically progresses. But if you ask that the lighter nuclei, do they split further? And no, that does not happen.
Okay, so the second question is, what if we don't add the fuel in the nuclear in time? What will happen then?
Sorry, could you repeat the question, please?
What if we don't add the fuel in the nuclear in time? What will happen then?
You mean if you don't refuel as per... well, see, is not just related to, to ensure that we have, a steady, it's not just to ensure that we have a steady power supply, but it's also because all these fuel bundles, like you saw in the video, so the fuel bundles which are being, kind of replaced, and the spent fuel is being removed, that is also to ensure that the casing, the metal zirconium casing that in which you've kept the fuel is, not damaged so much that it tends to release the radioactive elements into the reactor core. So the refueling, or the changing of the spent fuel and interchanging between the spent fuel and adding more new fuel rods is also to ensure that this sort of breach in the clad or breach in the clad does not occur, and the radioactivity does not release. So like when they say that a typical let's say if a typical limit is 5 to 6 years for a particular fuel bundle, it's not that you will use the same bundle for 5-6 years and then only change it. You have to keep on circulating in terms of using newer bundles, or maybe then again replacing the already used bundles once they've cooled down, so as to ensure that the integrity of the fuel bundle itself remains intact. Otherwise, it could lead to an accident.
Thank you, Dr. Vaishnavi. I have to say we are awestruck, and thank you for explaining to us the brilliant work that promising us clean energy. Dr. Nitendra Singh, I'd request you to say a few words on the visit.
Thank you so much, Daksh. I hope all of you have enjoyed it. So this is one of the drawback, or one of the many drawbacks we have faced due to the pandemic, due to the COVID-19 effect. We would be happy to take all of you to Tarapur or any other nuclear power plant or any other nuclear facility in person. But due to this pandemic scenarios, we have not been allowed to do so, which is, of course, safety is first. so we cannot have to have such visits. That's why we decided to have at least a virtual visit, which you can, like, at least you can see how things go and how a nuclear power plant looks like. So this is one, and similarly, due to this reason, and in France, we have the lockdown. The second lockdown started about a week ago. So the similar situation is here in the Iter France facility as well. However, we have also received the virtual visit, and Dr. Joyita Sinha uh, will be conducting that visit as well in her lecture, in her interactive session, so to say. So few things which Vaishnavi has already highlighted, and they are highlighted in the visit as well, that if you want to work at any nuclear facility or in the nuclear industry, the minimum qualification to join as the scientific officer or the technical officer is the bachelor's in engineering or the master's in science. However, if you can join the technical team after just class 12th as well. So in fact, for the moment, like presently, the vacancies are out. If you want to try, if you want to explore, you can go to NPCIL website, and I'll also ask IYNS team to share these vacancies on IYNS platforms. So yes, you can join nuclear industry at any level you want, but I would ask you to just study a bit further and join at the higher level, so that you can learn more, so you can explore more. It's an interesting field. You learn a lot. It's a multidisciplinary field. Nuclear is not just about you read about atoms and science and everything. You read when you design a nuclear reactor or any nuclear facility or a fusion facility, so to say, which you will see. So it's not just about you have to play with the nuclear fuel. You have the structure, you have the mechanical structure, you should know about the architecture, everything you include all together, then you need the electricity to be supplied to your home. So all these electrical applications, you have control systems, so all this electronic application, the computer science application, everything is come all together to realize this. So this is what I wanted to say about it, and I think this short visit has also clarified some aspect of spent fuel and how you manage the nuclear fuel cycle, which is the next session. So stay tuned for a few more glimpses in the day, coming in the day. Thank you, Daksh, and thank you. Yes, Vinita ma'am, want to add something, please?
I would like, thank you. I would like you to address what is written in message box by Shashi ma'am. So she's asking that yeah. So please check it and reply. Thank you.
Yeah, sure. Thank you. I'll just.
Should I read it out?
It will be nice because my chat box
Shashi ma'am has said it was intriguing that while their protective gear covered every other part of their body against radiation, but the face, eyes, nose were exposed till a certain area. Is there a reason that this is considered safe?
This is okay. This is a nice question, and I think it's a very astute observation by you, Shashi ma'am. So the protective layering which they have, they were wearing, it is not for protecting themselves through with the radiations or something like this. So these gears are not the protecting layer. It's like a simple industrial wear, like a jacket or a coat which covers everything. The idea is when you enter into into any reactor, any nuclear facility, I would say, then as in Jihan was mentioning yesterday, there is the possibility of contamination. For example, if you touch somewhere, there is some radioactivity, it can attach to your body somewhere where, and then you come out, you might interact with other people. Like the COVID, you can transfer it to other people. So to protect it, what you do, you wear all these gears, you go inside, and before coming outside, you remove all that uh, before coming within the facility itself. Then this protective gear and everything is treated equally as the radioactive waste. They monitor it properly if there is any radioactivity and anything, and they treat it properly before disposing it off. So once you remove all that stuff and come out, you are again being checked if there is any radioactivity or not, any contamination on your face, on your body. So it's completely to ensure that you are not carrying any contamination outside this facility. So the layering is not because of the radiations. I mean, to protect you from the radiations. The radiations are very well protected with the boundaries and the shielding, which is already being designed and being included in the design of any nuclear facility. So, as I always say, I have worked in the nuclear reactors for quite a long time. And I always say the nuclear reactor, inside the nuclear reactor is the safest place, I feel, because there you don't even have the UV rays coming from the sun. So you don't even have the sunburns, I would say. So that's how reactors are safe. Along with the minimum requirement, you add the adequate requirement to that limit, so as to make sure that even in any deviations, you have the safety in operation, in safety in any situation. So I hope I'm able to clarify it. So there's no issue. You can directly roam around just like that.
Thank you. Thank you, because this was a 7-year-old child near me who was observing and asked this question, and I thought it was important that it gets answered. Thank you so much.
It is my pleasure, ma'am. Thank you, Daksh. You can continue.
Yes, so let's take a short break for 5 minutes and let's rejuvenate while we watch some interesting feedback from our students.
My name is Abdul Kalam, and today I want to talk about my experience. I have learned the working of the nuclear reactor, the theory of thermodynamics and electromagnetism, and I have also understood many concepts of life.
Hi, this is Rakesh from Design Class. This was a very fruitful and interactive experience to understand that part of life
I am Tarapur from Shiv Nadar School, Hyderabad. The energy boot camp inspired me with wonderful opportunity in a short span of time. I learned many things about nuclear energy which I didn't know before, and completely changed the way I looked at it. Earlier, I used to be against nuclear energy because of the nuclear bombs and associated waste war, but I had no idea about its use in agriculture, medicine, and energy generation. I'm delighted to be part of this program. And the sessions provided by IYNS help a lot to learn along with fun. And the way Sun has related nuclear energy with our daily activities was awesome. Energy Boot Camp was one of the best programs I ever attended. And the program was full of learning and fun. And the best part of the program was the creation of the galaxy and the virtual nuclear reactors. Overall, I had a good time and it was wonderful. What I was expecting, it was more than that. The virtual learning experience was very sensitive and learned a lot from an expert. And the most important part is that I enjoyed every bit of the session and learned the experiment successfully. Thank you, Chef, for my legacy. The best side is always helping students in his activities with his innovative ideas. I inspired to think differently on complex science experiments. I was in contact with him weekly, and he made me think so deeply into the science. He posed such questions that made me think differently and scientifically. I made me research more and more in my experience. We are very thankful to him for making us better thinkers, and we would love to continue this process with him. He is extreme qualities for the courtesy, and there is this
Sorry. We played the experimental session by SNU children video in the break time. Thank you.
Sure, ma'am, just a second.
A very good morning to everyone. Today, we would like to officially announce the collaboration of the Physics Society of Shiv Nadar University and the STEM department from Shiv Nadar School, Noida. We plan to organize experimental demonstrations, interaction sessions, discussion sessions, quizzes, and various other activities with an estimated frequency of about once a month. Further, we would be happy to extend the collaboration with other branches of Shiv Nadar School, as suggested by Vinita ma'am. The aim would be to motivate and inspire young school children to appreciate the role of science in our daily lives and to spark an interest to pursue a career in scientific research. It's our pleasure to be an integral part of the collaboration.
And ready for the level of knowledge and learning. We still have a lot of stuff planned for fulfilling your curiosity and redefining your intellect.
Most of you would have a fairly good understanding of the biggest problem related to nuclear energy, that is nuclear waste. We know from experience that nuclear fuel needs to be disposed of very carefully because if radiation isn't concerned with utmost precaution, we risk thousands of lives and environmental damage. So, how do scientists deal with these dangers? What steps are taken to prevent incidents like Chernobyl? Our next session is going to be focusing on all this. I would like to invite Dr. Nitendra Singh, the founder and president of IYNS, a nuclear engineer by profession. His research interests include nuclear safety and design, reactor thermal hydraulics, and nuclear severe accidents. In addition, he's an avid speaker on nuclear for climate, advanced technologies, and public awareness. So, I request you to take the session forward.
Thank you so much, Sia, for this kind introduction. So today, actually, I am filling up for Dr. Mukesh, who was about to take the session on nuclear fuel cycle and waste management. But he, in his place where he is in hometown and stuck with no connectivity. So I'll just try to justice with his topic. Let me just share my presentation with you. Just let me know if it is visible so that I can continue.
Yes, sir, it's visible.
Great. Thank you so much. So let's begin the nuclear fuel cycle and waste management. Let's talk about it directly. So this is me. I'm Nitendra Singh, and you can find me at president.ivyns at Gmail for any query or anything. And this is uranium. So you can find me in mostly all nuclear reactors in similar fashion. As we all say, the nuclear pallets. So let's begin what nuclear fuel cycle basically means. So nuclear fuel cycle is basically you have you should have a fuel to be used, or as we say in technical terms, you should burn in a reactor to harness the energy, which can be used to produce electricity. And then once you are done with that fuel, you take this spent fuel or spent byproduct, or in some cases you can say this waste, and then take care of it. This is, if I remove the word nuclear, the fuel cycle is all about this. For example, in a coal plant, you add the trains of coal into the system. It heats up the boiler, it generate the steam and run the turbine, and then this ash which comes out of the plant just been dumped outside. So in the similar fashion, everything, if you use gas, it has its own fuel cycle. If you use other resources, it has its own fuel cycle. So similar way, we have nuclear fuel cycle. However, the nuclear fuel cycle is a bit different from the conventional fuel cycle, which I will share, which I'll discuss in this particular slide. And I would like to spend some time on it and take things slowly for you to understand what basically nuclear fuel cycle is. So as you all know, like any other element, most of the uranium is a metal which you can take out from the ore. So it's the story or the journey starts with the mining, with the ore you have, or as in some cases, or as I have mentioned here, soil to spirit. So you have this soil, as I say in a layman language. This ore is then, so you do the mining. First, you take out the uranium ore out of the mine, and then you do some processing of this uranium ore. it's some processing is done at site or near to the facility, and then there are some processing which is done in dedicated facilities, which is then after this processes, you get the uranium as the fuel, which you can actually use uh, by fabricating is in a particular shape, which I mentioned, like a pallet or so, which can be then used in a reactor to generate electricity. Once you are done with that, you cool it down, and then from here you take two paths, which you need to understand. So one is you started with the fresh fuel, and then you can once you are done with the harnessing the energy, you can cool it down. You pack it into a cask, and you can put it in the disposal facility. So this is called as open fuel cycle, because you started with this, and the starting and end points are not the same. So you can just once through, you call it once through fuel cycle. So this is the main one of the prominently used fuel cycle across the globe, like even the United States and many other big nations use this sort of fuel cycle. However, the country like India, we are a bit smart, I would say, and we use this cycle, which is this loop you can see, which we call it as closed fuel cycle. Now, what is the difference here? After burning it in reactor, or after utilizing the fuel in the reactor, you cool it down, okay? Then you send this cooled fuel to a reprocessing facility, and this reprocessing facility take out the reusable part out of it. So like it takes out the remaining uranium, it takes out the other uranium plutonium mixture, and then what is actually left, or what is the actual waste, then it send that waste only to the disposal facility. And this uranium is again processed in the initial chain, and then again sent to the fuel fabrication, and then again used in the reactor. So you can see you are able to keep using this fuel for long and long and long and long. Now you may ask, if that is the case, then what is the concern? Sorry. So and how you can do so? How much processing you can do? So the answer lies in the natural uranium. The natural uranium you're mining from here, and you're processing it until here, until the milling and conversion. So in the natural uranium, 99.3%, please remember, 99.3% is uranium-238, which is not fissile. It does not undergo fission. It does not split to give you energy. 99.3%, which is uranium-238. Okay. So what is the fuel actually is the 0.7% U-235, which undergo splitting, which is the fissile material, which undergo fission to give you energy. So imagine if you want to put, say for example, 100 grams of uranium into the reactor. So you are actually putting 99.3 grams of uranium-238 and 0.7 gram only the uranium-235. So this you need to understand. So in a reactor, once you are done, this uranium-235 only has been used, and due to the nuclear reactions, there are some changes in uranium-238, which by absorbing neutron give you plutonium-239, which is another fissile material which can undergo fission. So in a way, you are burning some fuel, but you are also gaining some fuel during these nuclear reactions. So all these things are happening in this closed fuel cycle thing. So once you decide to do the reprocessing, you can take out all that system. So this reprocessed uranium is basically that remaining uranium 238, U238, which you can reuse. And this uranium plutonium mixture, which I am saying, this is basically U235 and plutonium 239, two fissile material which can be directly sent to fuel fabrication. So, these sort of thing you can do by using a reprocessing facility, and you can close the cycle. And as Dr. Chidambaram has mentioned on quite some occasions and recently as well, that if you do the closed fuel cycle thing, then you actually make a nuclear energy a renewable energy, because then you even with the limited resources, you can multifold the duration for which you can use nuclear power, or you can harness the nuclear power. For example, if you have resources for 10 years in once through or the open-ended fuel cycle, you can multiply it maybe 10 or maybe 50 times to use the same number, same limited resource for the longer duration. So this is how it helps, or what differentiate the benefits of closed fuel cycle and the open fuel cycle in terms of the energy harness. The second thing, which is very important aspect here to see, so if you see in once through, your entire fuel is basically the waste. Entire fuel, whatever you use, it's coming down directly as the waste. I gave an example and I repeat that example once again. If you are drinking a Coke using this aluminum can, and if you throw this entire can as the waste, then imagine if you are drinking one Coke per day, then after a year you'll be having 365 cans. And you can imagine the volume you need to store that 365 aluminum cans. Second thing you can do is you can crush it down. You can compact it down with high forces and make it a small packet of aluminum cans which can be stored. Okay. The third thing which can be done is you melt it, remelt it. Then you can separate this paint and all which was there on, to color this beautifully. That will be your waste. And all that aluminum which was used to fabricate it earlier can be reused for the fabrication of cans. So, what is the amount of actual waste you are having through the closed fuel cycle, all the recycling process is very small amount of this paint. In the similar fashion, it happens in the case of nuclear fuel as well. If you reprocess it, you are reutilizing the remaining uranium. You are reutilizing the newly formed plutonium as well. And then you will be left a very small amount which has not been, which cannot be, for example, utilized, can be treated as the waste. So I hope this has given you some perspective. I can keep coming back or keep referring this this image again and again. So let's begin. Let's begin the journey of mining first. So I'll take step by step to explain all the elements of this cycle. In India, the mining and explorations are carried out by Atomic Mineral Directorate of Exploration and Research, AMD, and the mining and processing of the uranium is basically carried out by Uranium Corporation of India Limited, which is UCIL, and both are the subsidiaries of Department of Atomic Energy, DAE, in India. And there are some locations which are mentioned. So most of the uranium mines are in eastern part of India, in Bihar and Jharkhand region, in northeastern region, and some are in Karnataka and that belt. You also have some mines in Rajasthan and all, but they are of very small quality. So then, as I was mentioning, once you mine it, you basically process it in some stages, like this is the mine, the natural uranium, which you do some process, some chemical and some mechanical processes. Then you come up with this yellow cake. This is the yellow powder for a moment. Then you form the yellow cake, and then you convert it into possible fuel which can be used in the reactors. So this is the initial fuel processing of the fresh fuel you are having. Then you enrich it. So by enrichment, I mean to say, as I was mentioning, in the natural uranium, this is this is very nicely mentioned, 99.2% of uranium-238 and 0.72% of U-235, which I was mentioning. So if you want to use it in reactors, in certain type of reactors, you can increase this percentage of U-235 to 3 to 4%. This depend on type of reactor. For example, one type of reactor is pressurized heavy water reactor, which you have seen in the video at Tarapur. There you use the same uranium. You don't need to any enrichment in it. You directly put it inside the reactor. However, the reactor which recently we have got, like VVER, which is a PWR type, pressurized water reactor. There you use this type of fuel, which is enriched to 3 to 4% of uranium-235. And the reason is, which there was one question which asked, what if we don't refuel it? So nothing will happen. The reactor will continue because the bundle has a lot of power, then we harness out of it. But the only thing is, if we want to reduce the refueling in the PHWR type, you can do a continuous refueling or online refueling, as we say, even when the reactors are running. On the other hand, in PWR and other type where the vessel is closed, you need to open it before putting the new fuel. So in that case, you do this process after a year or after a year and a half of the refueling. So you want to make sure that you have enough fuel for this duration within the reactor. So this is how you come up with the idea of enrichment. Means you increase the percentage of fissile material within the existing fuel. Then the fuel fabrication. As I was mentioning, this yellow cake is then converted into some black powder with some chemical processes, and then it is formed into the pellet, which is about 7 grams. Then these pellets are basically inserted into a metal tube. You call it clad. It could be vertical, horizontal, depending on the time, and depending on the type of reactor. And then this basically rod or fuel pin is then collected or arranged in an assembly which is called as a fuel subassembly. And this number basically depend on the type of reactor. It's not completely based on this is not the standard number. Depending on different type, this configuration changes. In India, this is done at Nuclear Fuel Complex in Hyderabad. We have a dedicated facility which is also working under Department of Atomic Energy, and they generate all type of fuels for Indian nuclear program. Once this is done, type of fuels are then burned or then utilized in the reactors of different kind. Then you harness the energy, and then you are left with your spent fuel, whatever fuel. So in the video, I was loading 2 fuel bundles in the beginning, and then in the end, he was removing 2 bundles when they were discussing the spent fuel. So you can notice that depending on the different fuels, different reactors, you can have a different type of fuel, spent fuels, and they have different time duration for which they should be cooled. When I say cooled, what do you understand by cool? This you should know. Cooled means even if the reactor, the fuel is coming out of the reactor, it has the fission fragments or the fission products, as we say. So all these fission products are decaying or releasing radiations to coming to the stable state. So you need to give them time, as per their half-lives, so that they can decay all these radiations and then become cool in that sense. So, and you don't want to make sure that this radiation doesn't go out. So you keep it you take out the fuel from the reactor and you put them into such spent fuels where there's a lot of water and a lot of shielding is there. You just put the fuel there for some years and it stays there, and once it cools down, you can then take it to reprocessing. This is where you actually treat your waste. So now there are two possibilities. If you go back, you can go into two directions. One, this entire spent fuel can be treated as the waste, like your can, your Coke can, or you can reprocess it here and you can reuse all the elements which were there in it. So as I was mentioning, once coming out of the spent fuel, it can go for several processes of reprocessing. It is like a very complex system. That's why most of the nation avoid this reprocessing. But if you follow all this reprocessing, you mainly get some uranium products and you get some mixture of uranium and plutonium products, and you also get some waste which need to be treated again. So all these uranium products are directly fed into the processing, fuel processing, in the, as I was mentioning in the first picture in this cycle, and all these uranium plutonium mixture are directly sent to the fuel fabrication facilities where they can directly be included into the new fuel. I mean the fuel fabrication for reuse in. And if you are sending it directly to the waste repositories, then you just shield them into some specially designed canisters, and you can store it in a underground facility which looks mostly like this. This is designed mostly with the experience of international cooperation, and as you can see, there is a lot of shielding for the intermediate or low level waste which you can keep, and you can also keep like unshielded very intermediate level waste here, and you can have a properly shielded high level waste here, and it is very well below, if you can see from the surface of the earth, like very deep you put them, and then you have some access shaft where the concerned people only authorized people can only go for the monitoring and stuff. So this is the of how you may end up with the waste. But this is not how you treated it, okay? I am just saying how you end up with the waste. So this is how the basically nuclear fuel cycle functions. You have the mined ore, which you process it to make fuel pellets. These fuel pellets then are properly encapsulated in the clad, which is then used within the reactor for generating the power. And then this, after generating the power, it is cooled down into a spent fuel, and then after cooling you may have two options. One, you can put it directly into the waste repository. Second is the nuclear reprocessing facility, where you reprocess it, take out what is not being used, you reuse into the cycle again, so that you can reharness the remaining energy, and this closed loop and closed cycle is keep on continuing. You reduce the amount of waste in closed fuel cycle. So summary, I hope you understood. If you don't do this and you directly put it, okay, I'm done. I don't want this headache. It is very complicated. I have a lot of fuel. I have a lot of big reserves of uranium. I don't care of this reprocessing and stuff. I'll use it every day and put it like this and oh, I'm good to go. Then you come up with a lot of waste. And in any case, nuclear industry is one of the most accountable industry, as I always say, and I really appreciate and feel proud about it, which is accountable and take responsibility of its own waste. You know, as a human being, we should take our responsibility of our own waste, which even we very well educated people don't do. I have seen many examples while you're driving on highway and you see people eating the chips out of the Lays and they just threw it out of the window. So it is very, very important, and I feel proud, as I mentioned again, that you take responsibility of your waste. It is important. So let's dig in about what are the myths and what are the realities. So you need to understand, like nuclear industry generate a lot of variety of waste. It's not like everything coming out of nuclear industry is a very high level waste. You know, you have once it is coming out, everyone is dying outside. Nothing happens like that. You have many type of waste. The one example is low level waste. By low level means the radioactivity is very low, it's short lived. It will be like the half life is so small that maybe in couple of days it will be stable nuclei, it will no more be radioactive and stuff like that. And also the level of radiation is very low. So all these low level waste are generated from, for example, you have the X-ray department in each hospital, or you have the radiotherapy or the cancer treatment department in all the hospitals. You are dealing with the radioactive sources. You take out all that low level waste from there. You can also have low level waste from the universities. For example, there are universities where you teach, you use radioactive sources to study and to, you know, do some experiments, and you may deal with some sort of radiation sources. So there also you generate some low level waste. Or for example, you had a visit yesterday where New Year, where they are also dealing with some nuclear facility. So when there is some person who's going inside, or if they are opening the sources, they may come up with such sort. So all these small, and also from the nuclear fuel cycle. For example, the people who are working in the fuel fabrication, or as Ma'am has asked one nice question, this yellow thing which people are wearing, all this is the example of low level waste. So you can basically treat it properly, and then you wait for a while, and once you find it everything, so you can like a shallow bury it. You just put it in a really acquired and a designated place. You can put it safely, and after some time it's normal. It's normal to the to the background radiation, so it becomes safe. Sorry. Okay. So you also have some facilities which treat it such low level waste. You know, they processes, they collect all the waste from different facilities, and then they process it, and according to their processes, if it is needed to, you know, recycle it, they recycle it. If they needed to put it in a low level waste depositories, they put there. And they also take care of all the, you know, transport and everything. They also take care of, you know, how all these capacities can be managed and everything. So in India, this is all done by Department of Atomic Energy, and they all are very well regulated by Atomic Energy Regulatory Board, and they keep eye on everything what's going on and around. Waste canisters, this is one of the image you will be seeing everywhere, and everyone is saying this is the nuclear waste. It seems like, you know, this is the actual waste you see, and this is the actual waste coming out of the reactor. But let me tell you, this is the waste container which is used only for low level waste, or the medium level shielding inside such canisters. And the color and design is very well chosen. The color yellow and black. You might notice that the color of commercial vehicles, the taxis, the number plate, the color of number plate of the commercial vehicles in India is also black and yellow. And the reason is the black and yellow is the combination of colors your eyes can see very distinctively. So you can notice in any unforeseen event, you can identify this sort of canister. Okay, this is radioactive material, and you can stay be safe. So that's why this color and this design is very well chosen. Canisters also, you have a lot of shielding so that nothing goes out even while you're transporting it, or you are keeping it on public ports, for example, on railway station. Sometime you use this transportation via roads, via rail, shipping, everything. So you maintain the public safety. So these canisters are also very well designed. Now, coming to the actual thing, as I was mentioning earlier, it was the low level waste. But what about the high level waste, which we actually get from the reactor? So how high level waste can only come out of the reactor in the form of spent fuel. So now it depends if you are using or if you are defining your entire spent fuel as the waste, then you have the entire entire spent fuel as the high level waste. But if you do this reprocessing, then as I was mentioning, the 96% of this spent fuel can be recycled and can be reused. And the 4% is just the radioactive waste. So here I want to point out one more thing, like if you process this 4% in the second stage of Indian nuclear power program, which is where you're using breeding reactors, for example, there you can put this high level waste, and then you are mainly left with around 1% of the 3% of it will be used in that reactor, and 1% will be the actinides. Actually, high level waste components are the actinides, which will be then you need to treat. So you can imagine, out of this 100% spent fuel, only 1% is the actual remaining high level waste which you need to process. So as I was mentioning, you have this question mark, is nuclear waste actually a nuclear waste? And I still have not added here that even this 4%, out of this 4%, you take out all your isotopes for medical application. You know, all this cobalt 60 and everything which you saw yesterday's visit. All these sources are coming out of this 4%. You know, you take out medical sources, you take out industrial sources, you take out sources for the food irradiation, which Ganesh was mentioning. You take out sources for the agricultural application. You take out sources which you need for space exploration. Everything you take out, whatever is possible. And if you see, in the end, you will actually be left with only a 0.5% of the actual waste. And let me apprise you here that even this 0.5% of high level actinides, India is working on the technology where they can also be used as the fuel. So, you know, in the end, once we'll be succeeding in this complete fuel cycle with this new technology or a new type of reactor India is working on, then practically you will receive no high level radioactive waste out of nuclear industry. The only low level waste, which is like, as I mentioned, your clothing and other stuff will be, which is fuel cycle, which is coming, will be the actual waste. So I don't think nuclear waste is a concern. Okay, and I'll explain you why. So this is one of the example which I am all this discussion which I have done. So you can have, you know, the low level waste or medium level waste coming out of your fuel cycle, and you can put it in such different type of canisters, and then you can put it in the deep depositories, which I was mentioning. And this high level waste, which I was mentioning, this 0.5% or 1% of this waste is again vitrified, compressed and formed in the form of very packed system, and then shielded, multiple layer of shielding, and then it put within these deep depositories. And here you can see they have mentioned these are more than 300 meters below the surface, so that they are pretty safe for the public and for the people around. This is one of the example of these disposable canister I was talking about here. This is the radioactive waste which you very tightly pack it, and you put so many iron layer or steel layers around, and then you shield it in copper shell or in other metal shell, and you also give some space for some application of due to some heating and some processes. And then, as you can see, they are stored in different style into these depositories, and you can see you can just pass through from the entrance to the very deep through some zigzag paths, so that nothing can be reached directly to it. So that's how you basically process this entire nuclear waste or nuclear spent fuel, I would say. And in the end, the get is like this. For example, in France, which is generating 70% of its electricity through nuclear, they generate only 5 grams per year per inhabitant of the nuclear waste, which is nothing but the I don't know if you remember, there used to be a 25 paisa coin in India, almost of that size, very small coin size of the waste actually coming out of a nuclear reactor. So, and to give you some glimpse of it, I have one video. I hope it will give you some glimpse. Let's see.
Nuclear waste disposal. Deep geological repository. Types of geological repository for nuclear waste are mine repositories, very deep boreholes. This is example how is waste stored in repository. Later in video we will see 3D animation of complete process. In the early 1970s, an abandoned salt mine in Lyons, Kansas, is become only long-term geologic repository for nuclear waste in the United States. Repository received its first waste shipment in 1999. Since then, more than 90,000 cubic meters have come to rest here from around the U.S. Today example is Swedish repository. Nuclear power companies in Sweden jointly established the Swedish Nuclear Fuel and Waste Management Company, SKB, in the 1970s. SKB's assignment is to manage and dispose of all radioactive waste from Swedish nuclear power plants. SKB is responsible for a system of facilities used to handle all waste from the Swedish nuclear power plants. These facilities include a central interim storage facility for spent nuclear fuel near Oskarshamn, and a final repository for short-lived radioactive waste in Forsmark. Transport is by sea, using the vessel MS Sigrid. Almost any material can act as a shield from gamma or X-rays if used in sufficient amounts. Different types of ionizing radiation interact in different ways with shielding material. The effectiveness of shielding is dependent on the stopping power, which varies with the type and energy of radiation and the shielding material used. Shielding reduces the intensity of radiation depending on the thickness. This is an exponential relationship with gradually diminishing effect as equal slices of shielding material are added. In this 3D animation we will see how radioactive waste is delivered and stored in repository. This is example of high-level radioactive waste, but it can be used for all types of radioactive waste. Radioactive waste is stored in dry cask cylinder made from steel. Casks are transported from above ground to the deep repository. Deep repository must be made with quality of the rock mass, especially its fracturing, homogeneity and the strength of the overburden. Moreover, the subsequent alterations to these structures will be very diverse, depending on their purpose. Repository consists of various types of mine workings, pits, chimneys, inclined passageways, horizontal corridors, caverns, vertical shafts and small cross-section corridors. In caverns or vertical shafts, casks with radioactive waste will be placed and sealed with concrete or bitumen. Thank you for watching. Please subscribe.
So that's all from my side. I just want to tell you, like, nuclear waste is a very well regulated and very responsibly taken care by the nuclear industry, and it's not the concern. It is mainly dealt and managed very intelligently by the responsible people. So thank you so much. If you have any question, I'm open for that.
So we have some questions, but
Yes, please.
I believe it is time to move for the next session. Uranium and plutonium, and extensive research is being done to design a reactor operating solely on fusion. To familiarize us with the latest developments in the field of nuclear fusion, educate us about its future prospects, and take us on a live tour of the ITER fusion plant in France, we have Dr. Joyita Sinha. Dr. Joyita Sinha is a plasma physicist working in the ITER organization in France as a Monaco postdoctoral research fellow. She has done her PhD in physics from the Swiss Plasma Center, Switzerland. She has done her master's thesis from CERN, Switzerland, and has experience of working on different scientific projects in an international multicultural environment. Ma'am, over to you.
Yeah, thanks a lot for the introduction. So am I audible properly?
Yes.
Okay. Okay. So let me try to share my presentation. Let's go to the. Okay. So is it visible properly? Can you see the screen?
Yeah, ma'am, it's visible.
Okay. Okay. Wait. So first of all, I would like to thank the IYNS people for giving me this opportunity to talk to you people, and also thanks to your school as well. So let's start with the topic I'm going to talk today about. So I have tried to keep it as simple as possible so that it's easy to understand. So the topic I'm going to talk today about is fusion technology and reactor. Why do we want to use nuclear fusion as one of the ways to produce electricity? The reason for that being the following, as you see here. mentioned that there are no greenhouse gases, then it's a clean, renewable source of energy, because we use actually the isotopes of hydrogen, so deuterium or tritium in this process, so which are actually available, especially deuterium is available in the water, seawater and things like that. And then the last part is that we actually don't, one of the things about fusion, nuclear fusion, is that we don't generate the radioactive waste as such. Because we only use tritium, which is a radioactive element indeed, but it has a very short half-life, and that's why we reduce the amount of nuclear radioactive waste that is generated in this process. So before we begin with anything else, let's talk about the sun. As we all know that sun is the source of energy for us, right? And so the sun is actually the thing which powers the sun is in fact the nuclear fusion reactions, as we see. So the core of the sun is powered by this nuclear fusion reactions which occur in the sun. And that's how the sun actually gets its energy. So we want to create the same thing on Earth, actually, in this case. And that's what the aim of nuclear fusion is. So this is just an example which shows us the reaction. So here we have deuterium, which is an isotope of hydrogen, and tritium, another isotope we see here. And these two need to combine or fuse together to form as you see here, a reaction, a compound which is unstable, and then it gives you helium atom, as you see here, and a neutron. And in the process, we do release energy as well. So let's try to understand this process, that how does this fusion occur? So the thing is that this deuterium and tritium, as you see here, these have a positive charge. So this is like the positive nuclei you see here. And because of that, they try to repel each other. They don't like each other, as you see in this cartoons shown here, that they don't want to stay together. So they will always try to go in the opposite direction to each other. But in order to fuse, we need them to come together. So how do we do that? So that we achieve by giving them energy. So we try to give them more energy, heat it up, so that this energy actually tries to bring these two close together. So there is a force which is trying to bring it close together, and there's a force which is trying to go in the opposite direction, bring them apart. And then when you actually finally give sufficient energy or heat it sufficiently, then finally we will be able to overcome this force, which is which is trying to move them apart, and we finally are able to fuse them, and we get fusion reaction. So this compound here. But I would like to point out that this energy I'm talking about, or the heat I say we need to give, is actually pretty high. So we actually need temperatures which is of the order of around 150 million degrees Celsius. So you can imagine that it's very high. So that's why this is something which is very important in our case. So now just showing you, so as I mentioned before, that we have the product now, the fusion product, and then we would get from this, the helium or alpha particle, as we call it. So this also will carry a part of the energy, and a part of the energy will be carried by this neutron. And this is the energy that is carried by this neutron will be actually used to produce the electricity. Whereas the energy which is carried by this alpha particle or helium will be actually used to self-heat or provide, heating for the reaction, fusion reaction to go on. So this is the process that is planned to occur for a nuclear fusion reactor when we try to make one. So now, as I mentioned before to you, that we do have very high temperatures needed for these reactions to occur. So this introduces us to the concept of plasma. So what is plasma? We know that typically the three states of matter, right? So we have the solid, like for example, you see here the ice. We heat it, then we get the water, which is the liquid state, and then we heat it further, then we get the gas or the steam, like you see here. So now if we heat the gas further, we give more energy to it, then we get a plasma. So that's the fourth state of matter. And plasma is nothing, basically it's ionized gas. So you give them sufficient, so much energy that your, atom actually dissociates into the ions and electrons, as you see here. And the examples of this is something that we see in our normal life is like the lightning. That's actually a plasma, or the sun or stars we have, they are also made of plasma. And we also in this, like I show you here an image which is of a welding process, which is also produces the plasma here, as you see here. So now the next question is that since it is so high temperature, so how do we try to keep this plasma, because it's very hot, right? So in order to keep this plasma in a container, we need to think how can we do that, because of these high temperatures, because everything will melt otherwise. So in the sun, it's easy, right? Because so in the sun, how do we do it? Contain this plasma? Well, the answer is it's actually because of the gravitational force. So there is a very high gravitational force, as you see here. So this is the thing which is trying to go out. The particles are trying to move out, your electrons and ions, but then the gravitational force of the sun itself is putting it back in place. So this is how we keep them the reactions going on, and we have the fusion and the power fuel which is powering our sun. But obviously we don't have that on Earth. So how can we do that? There are different ways, and I'll here be talking about one of the ways only. And so the one of the ways that we are pursuing at Iter, for example, is an example of that way, is actually to use the magnetic field. So the solution is actually use the magnetic field. So as we saw already that there are actually electrons and ions. So you have the positive and the negative charge shown here. And you might know, or even if you don't know, let me just introduce you that usually when we have a magnetic field, these electrons or ions, so the positive or negative charge shown here, actually usually rotate or move along the this magnetic field line. So there's a certain motion they do, as you see here. So they are like going around this magnetic field line, this blue line shown here. And this is the concept which is actually used in the concept of the nuclear reactor that I'm going to talk about, and which is what ITER is trying to do as well. And how the point is that if you have a straight magnetic field like this, then you can still lose your these electrons and ions, but that's not useful because then you won't have your fusion reaction. Especially you need these positive ions you see here to fuse. So what do you do now? What's the solution to this? So turns out the solution is actually not that difficult. The easiest way was that we actually close this line, so that we make a line, this magnetic field line, which is closed on itself like a ring, So we make a ring, a magnetic ring. And because it's now in this ring, they always move along this ring only. They don't go out. They remain within this ring. And in this way, we contain this plasma so that it does not touch any material surface, And we don't have these high temperatures touching the material so that they melt your container, in which you're trying to make. And this is the concept that introduces us to the concept of a tokamak, or a tokamak reactor as you want, which is the simplest way to explain it to you is actually it's like a donut, as you see here. So this is like a donut shaped thing you see here. And what we have here is the machine, the real machine, the schematic of it shown to you. So where we have here this pink color thing you see is actually your plasma. And the rest of the things are your different coils which will generate this magnetic field so that it's able to contain this plasma. And as you can see, the plasma is not touching these magnets or anything. So that's how we try to contain this plasma in this container, which is a donut shaped machine called as tokamak. So this is one of the ways we are using in fusion to create our fusion reactor, or let's say to create our sun on earth, as we say. So now, one of the things I would like to point out is that there is a thing that the bigger the size of this donut is, the better it is to produce fusion. Obviously, there's a lot of physics involved in it, but I think it would be too complicated to explain right now, so I don't go into the details of it. For you, it's just enough to know that the bigger the size of this machine, the better it is, and the closer we are to achieve this target of getting electricity from. So here, I'm showing you a very small tokamak, or let's say this machine, which is called Aditya, which we have in India itself, and it's actually located in Gujarat, near Ahmedabad, so in Bhat, in the Institute of Plasma Research, so IPR. And they have another machine which is called SST1. So this is the next step they have. And now I'll show you some of the other bigger machines we have in the world. So we have JET. Now you can see the volume of this is much larger than that if you compare. It's like around 80 meter cubed. So it's much larger in size compared to this one. And so this JET is basically a tokamak which is located, or a machine which is located in UK, so in Oxford actually. And it's called as the Joint European Tokamak. So it's initiative which by the European Union, different members of the European Union, to experimentally try to see that how we can achieve this nuclear fusion. The next step was to have this another reactor, which is called a JT60SA. Now this is located in Japan, and it's built in collaboration with the European Union as well as Japan. And it actually just started operation this year itself. And now we come to Iter, which is supposed to be much bigger than these ones. As you can see, the number here is much larger. It's like 800. And it's supposed to actually produce all these reactors. Before this, I showed you, they were experimental reactors, and they were not actually aimed to produce any thermal power. But this reactor Iter we are building, which is being built in France right now, is actually built with an international collaboration. And in the next slide, I'll show you countries involved in it. But as you see that this is supposed to have around 500 megawatt thermal power to generate this. So this will be the aim, where the first time we try to show, the fusion community tries to show that we can actually produce electricity using nuclear fusion. And then once we have shown this, for which a lot of countries in the world have collaborated, then the next step will be demo, which every country usually will be making by themselves. And it would produce even larger, as you see here, like around 2000 to 4000 megawatt thermal power. And the size will also be much bigger than ITER itself. And this will be the step where we build the fusion reactor and start to produce electricity using it. So now coming to ITER, as I said, that ITER is an international project which is with the collaboration of, as I mentioned here, like 35 countries. And we see here in this logo, the ITER logo, you see here the main countries. So we have China, the European Union, India as well. India is a part of it. Then Japan, Korea, Russia, and USA. So these are the major members of the Iter project. And here you see a schematic which is showing you the Iter tokamak. And this here you see this red circle here is actually man. So you can see the size of this building is very large. This machine is very large. So it's supposed to be a 30 by 30 meter machine, the whole building, this machine here. And the pink thing again here is your plasma, and the rest of the things are the parts of the machine that you see here. The container which is containing this plasma. And now I would like to show you a picture of, it's right now under construction, and it's being, this ITER site is actually located in France, where I am right now. And let's see how it looks. So this is how it looks. It's one of the recent pictures taken of the ITER site. This here is showing you the building, which is the tokamak building itself, so the reactor building. And these are, the other subsidiary buildings which are being built. So right now, I would say like more than 70% of the construction is finished, and actually assembly phase, assembling of, the different parts have started. So one of the interesting things about ITER is actually each of the components of this reactor that I showed you are being built by the different member countries of the project. So like India is making quite some parts as well, which we will show see in the coming videos. And now lastly, as I showed you before, so this is the final plan where we have a nuclear fusion reactor, and we can actually put it to the grid and generate electricity. So that's all from my side, and thanks a lot for your attention. So if you have any questions or queries, please feel me that.
Yeah, ma'am, I found a few questions and
yes,
it's
sure.
pretty fascinating. So first question is, ma'am, as in the intro, we got to know that only fission is currently used, but I know about particle accelerators that smash protons. So can't we use the same model, but instead of protons, we use whole atoms to make fusion reaction?
Yeah, so the thing is that, there are different concepts. So there is actually a concept like the question that was asked, that can we actually use particle accelerators? Yes, you can. But that's not the line right now pursued, let's say, by the most of the fusion community, I would like to point out. But that is one of the lines also some of the people have that thinking, which is like actually going for a hybrid where you have a particle accelerator and you use that to get your, nuclear fusion reactor. That's one of the concepts which is like, right now, let's say I would say maybe in discussion among smaller groups. But it's more, I would say it's a more, let's say the scientific community in the fusion side right now follow this one thing, which is followed is this magnetic thing I showed you. There's another one which is actually using lasers. So they use this inertial confinement, we call it, and actually you use laser to make this fusion reaction. So that line is being pursued actually quite extensively, I would say, in US. Like there are labs who have been doing quite a lot of work in that in US, and especially I think in Lawrence Livermore, that's where they have been doing a lot of work there. And even in Europe, there are labs which are working on that. And the concept of this particle accelerator, that's like, kind of a hybrid thing that is being thought of, but it's not yet, I would say, a widespread thing that the community has accepted and started to work on. But maybe in future, like we hope that in future, these kind of ideas that are being floated right now come into, actually people start to work in and build these things. So, yeah.
I think that was the only question right now. So
Mm-hmm.
thank you, ma'am.
Yeah.
Sure, the students are going to sleep on some of the ideas that you've left them with. And that was the last event for today. It's been a great journey. Yes, ma'am.
Yes.
Yeah.
May I speak here?
Yeah, ma'am.
So, Sachit, we have to go for virtual visit, ITR. This is the most
Right.
exciting part of our journey
Right.
right now. Thank you, Ms. Dr. Jaita. Thanks.
Thank
Yeah.
you, ma'am.
Thank you. Yeah. So let me try to see if this works properly or not.
In the meantime, if there is any question, please you can ask. Dr. Nitendra is here to address in
Sure.
the message box. So there is a question for you, Dr. Nitendra, in my message box
Yes.
from a student of, I think, grade 7. What he writes in WhatsApp. He's asking if the nuclear fusion reaction is not producing much of waste, then why don't we popularize this more than nuclear fission reactor? And also he is adding that we have nuclear submarine in India. What type of reactor is installed in nuclear submarine? Thank you.
Thank you, ma'am. I'll take these two questions separately. So first, very nicely mentioned, but if you see, which is very practical to see, the first commercial fission reactor came in 1950s. Okay, so we are producing commercial fission electricity from 1950s, almost 70 years now. Oh, okay. And fusion, as Joyita has already mentioned, we are still, so Iter is still a test reactor. The power which we are generating, the thermal power, we are not supplying it to the commercial grid. So we are still one step back from the commercial fusion to come up with. So this is one. Secondly, the fusion is still not easy to pursue. If you can see, there are so many studies, and Joyita has already mentioned there are many complexities involved in terms of technology, in terms of physics and science, and also in which is very important you to understand in terms of materials, because as she has mentioned, you have a lot of high temperature system. In here, the temperature means the high energy system. So you need to have a special materials to take care of it. And along with that, you also need to have a very high magnetic field to confine it. And to have such sort of high magnetic field, you need to have a specialized electromagnets which can produce this field, and they are mainly superconducting coils which can generate such magnetic field. And you know, superconductivity, it is itself an area of research and still growing together. So this is two. And third aspect which you need to understand, that during the fusion reaction, nuclear fusion reaction, you when you fuse to, for example, here DT, deuterium and tritium nuclei, when you fuse them, you once they are fused, they are again energetic particle, you know, and they decay to get stabilized as the alpha particle, and they release one energetic neutron of 14 MeV. And 14 MeV is such a high energy to, you know, it's almost unstoppable by any means. And you actually use that 14 MeV electron, that 14 MeV neutron to convert this fusion energy to electricity. And so that is one of the concern. If so, imagine this 14 MeV neutron interacting with any material. So far, this is one of the major challenge for the fusion industry, to how to take care of this material degradation due to this aspect of nuclear radiations. So in a way, nuclear fission and fusion, they both are not different things. The only thing is the advancement in the technology which we have so far. So that's why the entire nuclear community is focusing more on nuclear fusion, if we could have it commercially viable. And this is one of the reason, as Joyita has mentioned, why everyone is focusing more on tokamak model, not on the laser or the linear confinement model, because commercially this is more viable. So that's how it is. And nuclear entire community is willing and waiting and will be happy to promote fusion, of course, because yes, it produces very less high level waste. I want to emphasize on high level waste because, as I mentioned in the presentation, the main high level waste is coming out of the spent fuel, which we are using in fission reactors. And here in the, if you see the spent, the main fuel is nothing but the gas in a way. The plasma is nothing but the ionized gas. So the only secondary waste you get, but you don't give any high level waste. So that's why, yes, indeed, it's a clean energy and we all support it and we all promote it. Coming to your second question, yes, not only in India, in across the globe, everyone have submarines, which are also using a small and compact nuclear reactors. In these nuclear reactor, in these submarines, the type of nuclear reactor is mainly pressurized water reactor, PWRs. Why PWR? Because most of the reactors across the globe, if you see, for the moment there are almost 438 nuclear fission reactors working across the globe. So most of the most preferable type across the globe is the PWR. So the working experience the entire nuclear industry has is the most with PWRs. So when you feel like you have low maintenance possibility, like submarines are, when they are out, they don't come out in a year or two, or maybe in tens of years they'll come back. So PWR is the least maintenance system because of the experience the industry have. They produce it in this manner. So yes, all these submarines mostly use PWRs, pressurized water reactors. If I may have asked you, and I think, Joyita, are you ready for the?
Yeah. Thank you, Dr. Nitendra.
My pleasure, ma'am. Over to you, Joyita. Let's go ahead. We cannot hear you. I think when you share your this, you have to make sure that you include your system sound, and then you can.
Yeah, I am. Can you hear me now?
Yes.
Okay, include system sound. And we start with. Do you see the video?
Yes.
Okay.
Thank you.
Yes, thank you.
Iter, the world's largest tokamak, will demonstrate the scientific and technical feasibility of fusion power. 30 meters in diameter and nearly as many in height, the Iter tokamak is a marvel of engineering, created from an estimated 1 million component. The size and weight of the major components, the tiny tolerances for the assembly of major systems, the diversity of manufacturers, the tight schedule, all of these elements combine to make Iter an engineering and logistics challenge of enormous proportions. It was in November 2006 when the 7 Iter partners gave the starting signal for one of the largest international scientific endeavors ever attempted. Soon after, diggers and scrapers moved in to prepare the 180-hectare stage. And here we are today, 14 years into official starts of machine assembly. Despite the challenges of the COVID-19 pandemic, we have managed to maintain critical activities on the worksite, including the reception of a number of Iter's exceptional, first-of-a-kind components. In March, the European domestic agency, Fusion for Energy, put the finishing touches on Iter's assembly theatre. A vast hall for preparing, then installing machine components. In April, the first 2 toroidal field coils, Superconducting magnets weighing 360 tons each arrived from Italy and Japan. In May, the 1,250-ton cryostat base, supplied by India, was successfully positioned in the tokamak pit. Late June, the first ring-shaped colloidal field coil procured by Europe arrived from its manufacturing site in Hefei, China. Russia and the United States are also progressing in the procurement of critical path components for Iter. Finally, the first sector of the Iter vacuum vessel shipped by South Korea has arrived on French soil and will soon be transported along the Iter itinerary to the worksite. The buildings and infrastructure needed for first plasma are 75% complete, and the pace on planet Iter is picking up as machine and plant components arrive from the 7 Iter members. The time has come to put the world's largest puzzle together, the assembly of the Iter machine. Following the spectacular lowering of the cryostat base, the further assembly of the Iter tokamak will proceed in a bottom-up fashion. Machine installation will continue with the lower cryostat components, the lower thermal shields, and the temporary support structures for colloidal field coil number 6. A set of spare pre-compression rings are the next in line, followed by the central support structure and the 8 meters huge toroidal field coils. Thermal shields that will help protect the superconducting coils are attached, and finally, colloidal field coil number 6 is lowered into the pit, followed by colloidal field coil number 5. In order to prepare for the arrival of the pre-assembled vessel sectors, an inner support column, a work floor, and 7 radial beams are put in place to stabilize the structure during assembly and welding. While the lower cryostat components are being assembled and welded in the tokamak pit, 2 giants are standing in weights in the adjacent assembly hall. Standing 6 stories high, the purpose-built sub-assembly tools will suspend each of the 9 sectors of the vacuum vessel in turn, while thermal shield panels and toroidal field coils are rotated into position. By the end of this year, the first completed transferred to the tokamak pit. 8 others will follow. Last in line is the 18-meter tall central solenoid. The powerful electromagnet will be the last major component to be installed in the machine pit before the cryostat is closed up. Dozens of custom tools will be required to assemble, lift, and finally maneuver Iter's super-sized components. The tools will have a range of lift capacities, 500 tons for the upending tool that will turn vacuum vessel components from horizontal to vertical, and 1,500 tons for the heavy lift cranes that will carry all major tokamak components into the tokamak pit for assembly and welding. The precise alignment of Iter's largest and heaviest components to within tolerances of 2 to 3 millimeters is essential to the successful operation of the machine. Assembly sequences have been planned with this in mind and will utilize sophisticated optical metrology techniques at each step of the assembly process. The closure of the cryostat by late 2024 will mark the end of the first assembly phase. The Iter machine will undergo 1 year of integrated commissioning and testing, culminating in first plasma at the end of 2025. Beyond its symbolic importance, Iter's first plasma will be an important trial run for this occasion to verify the correct alignment of the machine's magnetic fields and the correct functioning of key systems. The very first low-power hydrogen plasma, lasting only a few milliseconds, will be followed by other shots of increasing power and duration. This shakedown mode, lasting a few months, will be followed by a shutdown phase. during which key systems for hydrogen and helium plasmas at nominal power are installed inside the vessel, such as the blankets, the diverter and in-vessel coils. These components will be introduced through dedicated port cells in the vacuum vessel, requiring a whole host of custom-made tools, work platforms and cranes. The world will be watching as decades of planning come to fruition, and the Iter tokamak is assembled from components shipped from all around the world by the 7 Iter members. Iter, leading the way towards a new, safe source of energy.
Thank you, ma'am. I think the 2 was what everybody was looking forward to.
Jyota, the voice is not coming.
It's not coming?
Yeah. If you can check it,
Okay.
please. Thank you.
Yes, I'm checking. Just a minute. Let me reshare. No.
A huge amount of energy. The energy we will then use to actually produce electricity. It sounds simple because stars have been burning on fusion for billions of years.
It's the fundamental energy of the universe.
But we need to control it on Earth. Here we are
it's Iter. Iter is a large international program in order to demonstrate the feasibility of fusion technologies.
Probably one of the biggest scientific and technological challenges that human race had to face.
In the sun, the pressure is very high.
To get that same kind of collision of nuclei, we need really high temperatures.
150 million degrees in Iter.
It's quite hot.
Probably going to be the hottest point in the universe right here in Cadarache.
You can't really make the same scale of the sun on Earth. We have to use a special device called a tokamak, which is basically like a donut.
So we are now constructing the whole platform and then starting to construct the machine itself before we can actually use it.
Here you have the tokamak.
The plasma is the state of the hydrogen when you heat them and you produce fusion power.
So you can think of a plasma as a ring of lightning, if you wish, which is traveling around the machine, held in place by strong magnets.
There is many challenging technology to have to be assembled and working all together, and it is a challenge we have to face.
So where I stand, there will be the vacuum vessel, okay? And attached to the vacuum vessel, you will have 440 modules of the blanket covering all the vacuum vessel and facing the plasma, and roughly about 600 meters square in area.
Basically, the main fuel source will be seawater.
This huge machine is fueled by this tiny pellet. We are now making things which have never been done before.
Just to give you an idea, these neutrons have so much energy, there was nothing to stop them. If it was in space, it will travel from here to the moon in 8 seconds.
There is, like I would say, a miracle around Iter.
It's always shown that the planet is able to collaborate on a scale somewhat above the normal argument level.
It's more than 30,000 people all over the world working in order to deliver and manufacture the different components.
Obviously, it's quite a challenge to keep the plasma contained inside a tokamak. So to do that, we need some super strong superconducting magnets.
This is the superconducting cable to be wound in a circle shape.
So the largest magnets that have ever been manufactured in the world.
You need these very large magnetic cages in order to maintain this 150 million degrees plasma away from the wall.
The magnets are super cooled because they have to be really strong. They're one of the coldest things in the universe.
So in 10 meters, you go from near the absolute zero to 150 million degrees. I can't imagine anywhere in space where you can find this kind of gradient.
As a scientist, I have been looking for this technology for several decades.
Everybody knows what they're doing, they're just going to get on and do it.
If we succeed, okay, it will be a real breakthrough for the energy supply for the world, not just a century, but millions of years.
We really need to work on this as soon as possible and prove this as soon as possible.
Future energy issue will be on our shoulders.
If we don't then prove that fusion is a possibility, then I think that this as an energy source for the future will be lost.
And now we as a team need to prove that we can do what we promise.
A dream is just getting reality.
If Iter works, you have demonstrated that you can create large amount of power from fusion reaction, and it gives rise to the hope of designing then fusion reactors which can produce electricity in the future.
If we master it in an efficient way, we have no more problem with any energy issue.
Samyak, this has already been played.
Welcome to Iter. Here in south of France, 35 nations are collaborating to build and operate the Iter tokamak, the most complex machine ever. We are recruiting candidates from all the countries involved in the project. Today, I'm pleased to introduce you our Indian community.
Nice to see you.
Nice to see you too. Nice. I am Site Construction Deputy Director. I am responsible for every aspect of the construction of the Iter.
This is how
it has been extremely enriching experience for me because first of all, various culture that is all at one place, various working methods and knowledge is all pooled at one place. So many brains are working together people across the globe are developing technologies and they are all bringing at one place. So this is a reservoir of extensive knowledge and wisdom and skills. It's a fortune to be in a place like this.
My job position here, I am the division head of the cooling system engineering. I have worked in Japan many times. I have worked a little bit in Germany, in US. For me, environment was individual at that time. And in Iter, it's a collective environment of internationality. Okay, so it is not any 35 nation nationality, it is Iter nationality for me.
Myself, Anil Bharadwaj. I am Group Leader and Technical Responsible Officer of Iter Cryostate. I am working for Iter project since 10 years, but I joined Iter organizations 2.5 years back.
We are going now to meet with Mr. Kumar and John, and together we'll go on the worksite to visit one of the most important buildings, the tokamak complex.
Not proceed till the procedure is fully. The working environment inside the Iter is very good. Even though there are challenges because of the various cultures which are there, the countries which represent half of the population of the globe, they are all at Iter. And then we are in a position to work together. It's a fascinating experience and very enriching experience.
For me, Iter is just not a project. Iter is an opportunity to learn. People should grab this opportunity, to prove themselves that they are their own engineering, their own technology, own knowledge of science to Iter. And this is only one-time opportunity, and it should not be missed. It should not be missed.
Good morning.
Hello.
Hi, nice to meet you.
And I got a full support of welcome office for relocation, for other services, for the schools, for the HR. So it was a completely smooth transition.
We first decided to live in NAX and we saw lots of houses in NAX. But since larger Indian community was there in Manosque, so we stayed in Manosque. Of course, we felt extremely relaxed and didn't find it at all any difficulty to go to the market, to mix with the people.
The good side of living in Provence is the landscapes are very pretty, very beautiful. The air, the water is so pure and fresh, no pollution. Every season it's very beautiful. There are about 25 Indian families here. They find out every single reason to have a party, to have fun, to dress up. I think we are much closer than as we were in India.
Only children, come on. The international school in the Manosque is very good for all people who are coming from the different countries. It gives all opportunities in their languages to study, and also gives very good foundation to study the local language and the other subjects, and they support us very well and our children for their studies.
हम सबको चाहिए कि ईटर आके के ज्वाइन करें और यहाँ से कुछ सीखें और सीख करके अपने देश का भला करें। ये हमारे लिए बहुत ज़रूरी है।
आप ईटर में आके आपका जो भी इंजीनियरिंग नॉलेज है उसको दुनिया के सामने रखिए। इससे अच्छा मौका और नहीं मिलेगा।
मेरा भारतवासियों से अनुरोध है कि मानव जाति के विकास के लिए ईटर प्रोजेक्ट को ज्वाइन करें।
Thank you, ma'am, for the virtual tour. And that was the last event for today. It's been a great journey so far and hopefully an enriching one for all of you. I'd like to call upon Mr. Raymond Fernandez, Director of Education, Shiv Nadar School, for the concluding remarks.
Can you hear me? Thank you so much. It was an incredible day. I'm running short of words, to be honest with you. We went from fission to fusion. We went from energy that was in the pipeline and being generated for such a long to catering to what we would be doing in the present, to a glimpse of the future. And I think this entire journey over a month and especially this day has been very enriching. And what it brings to us is a lot of hope. It is great to see that young minds from all 5 campuses and from the university have come together to join hands to see how we can most probably better a future. Energies, sustainability, security of energies are questions that as kids we never asked ourselves, right? From an education perspective, and now our students are being exposed to it. It has been a fantastic day for me. A lot of learning, and especially to see how India is contributing and walking hand in hand with the rest of the world. True, wonderful. I'm Ms. Vinita for making this possible. Also, Dr. for being with us all throughout. I enjoyed it. It was fantastic, and all the speakers. I'm looking forward to tomorrow. I believe we would be having quite a power-packed day. We would be asking some tough questions of each other. So I'm really looking forward to that. Thank you so much. I hand it over to you now. Best of luck.
Tomorrow is the concluding day of the Energy Boot Camp, and it is packed with the most alluring events. Final rounds of the inter-school competition will be held tomorrow, including the Special Youth Parliament that will be attended by experienced panelists and students of remarkable intellect. It's a day not to be missed, as there will be a good amount to learn and opportunities to put forward your views on sustainable energy. We look forward to seeing all of you tomorrow. Thank you.
We all look forward to seeing you tomorrow, and hopefully you'll come back with the same energy you've come today. And just before we call it a day, I'd like Shashi ma'am to share a few words.
Rajit, this was a sudden thing. I was just typing in to say how much I'm looking forward, as Raymond said, to the magical Sunday ahead. You know, for a person who knows the least, it is the most awe-inspiring, but also to the person who knows the most, as the inversely proportionate knowledge circle, there is so much more that you don't know, and that is the most fascinating part about life. But I would like to go back to the first day, when I think it was a member from the Nuclear Society, the IYNS, who said, and it was Dr. Singh who endorsed it, to say all of us, not just the youngest explorers, but everyone has to keep thinking out of the box, keep looking for solutions beyond the obvious, the predictable, and the ordinary. So thank you so much, Dr. Ritendra Singh, Vinita, Sachit, Sia, Dr. Joyita Sinha, and Raymond. You and I, along with all the others here, are going to wait with bated breath for tomorrow, along with the 2,000 odd students and so much that is happening. The 15 scientists and more, and all of you. If education was to happen the way it is happening now, Vinitha, I don't think there'd be any complaints from the secondary school all over the world, because that's exactly what they want to do. And I'm sure this is only the beginning. Thank you so much.
Thank you, ma'am.
Sachit and Sia and the whole lot of you, Daksh and Aditya, Kulshresht and everyone else, and Uday Bhan, as Raymond sir said, what you're doing today, we could never have dreamt, but there's no comparison. You are the people who will lead us into the future. And you have so many guides and so many people in the form of scientists. What comes to my mind, though Stephen Hawking never believed in something called God part, but he just said science and spirituality is the way forward. And those would be my last two little offerings. So science and spirituality, and I wish all our politicians and all over the world, everyone just got into track and could spend the money on these things rather than the others that take the world by storm. That's my prayer and wish. Thank you. Thank you, Vinitha. Over to all of you. Thank you.
Thanks. So, Sachit, are we going to end now?
Yes, ma'am. We're done for the day. Now we'll hopefully.
Thank you so much. Special thank to all the scientists who are joining from different time zone, because the time difference is so that when we start 9 a.m. in morning, you have to be there at 4 a.m. or something like that. So my special thanks to Dr. Nitendra and Dr. Jayati and all those, connecting from France. And it really has touched me that you guys were available since 3 a.m. because I was coordinating with you. For me, it was 8, but for you, it was something different. Thank you so much.
The pleasure is all mine, I would say. And on behalf of the entire team, I take this opportunity to see you tomorrow. And we'll see what comes tomorrow. Thank you. Take care. Stay safe. See you tomorrow.
Thank you, sir.
Thank you very much. Bye-bye.
Bye-bye.